Okay. So, all right. There is one announcement. As per the circular received from Government of Telangana, from 1st September, we are starting the offline classes. These offline classes are only for the students who have already taken the admission for the offline classes or the offline batches. Okay. But suppose you already you took the admission for the offline classes or the offline batches, and suppose due to the some personal reason or maybe any cause, if it is not possible for you to attend the classes at the Hyderabad location, then you can continue into the online mode also, right? So online mode classes will be going on simultaneously, right? For any additional information, you can contact the given number, right? Yes. Okay. Yeah. So next, in the yesterday session, we discussed about single phase half wave uncontrolled rectifier. Now we are going to discuss the single phase half wave controlled rectifier. Single phase half wave controlled rectifier, right? Okay. Am I audible? Right? Okay. Okay. Imtiaz, please check your internet connection once. Okay. Yeah. Okay. Yes. Yeah. So single phase half wave controlled rectifier we are going to discuss. So as the name here is controlled rectifiers, okay, controlled rectifiers. So here we are going to use the controlled switch, that is a thyristor. So let us discuss first single phase half wave controlled rectifier. HWCR means half wave controlled rectifier. Okay. Suppose the load is purely resistive load with a R load, right? So circuit diagram will be same. We're having a single phase AC supply, next the controlled switch and the load. Okay, so only three elements will be there. Yes, single phase AC supply. Here it is a thyristor, and here it is a load. Load is a purely resistive. Voltage across load is a V0. Current flowing through the load is I0. Voltage across thyristor is Vt. Current flowing through thyristor is a IT. Let us consider the source current is Is. Okay. So Vs is equal to Vm into sine of omega t. So it is a pure sinusoidal supply. This is a Vs. Next, as thyristor is a controlled switch, we are going to apply the gate pulse. Suppose at this instant we are applying the gate pulse to thyristor. It's alpha. Suppose this is 2 pi plus alpha. Next, voltage across load V0 and current flowing through the load I0. Right? This is the waveform of V0. The red one is for I0. Okay. Alpha phi 2 pi plus alpha. And it is a 3 pi. Let me draw the waveform for Vt also. Alpha pi 2 pi 2 pi plus alpha and 3 pi, right? So yeah, so here we are having a circuitry for single phase half wave controlled rectifier. We are going to discuss it for the purely resistive load first. Okay, so in the circuit we are having a single phase AC supply, which is a Vs. Vs is equal to Vm into sine of omega t. It is a pure sinusoidal supply, right? It is a pure sinusoidal supply. Okay, next, Is is the source current or the supply current. Load is a purely resistive. Voltage across load is a V0. Voltage across load is said to be positive if the polarity will be plus here and minus here. Means this terminal is at a higher potential compared to that of this terminal. Then we are going to consider V0 is positive. Otherwise, the V0 will be negative. Next, current flowing through the load is a I0. Voltage across the thyristor is a Vt, right? This is the anode of thyristor. Here it is a cathode of thyristor. Okay, and the Vt will be positive when anode will be at a more potential than that of the cathode. Okay, so Vt, and current flowing through thyristor is a It, right? Next, now let us discuss the circuit operation. So from as Vs is equal to Vm sin omega t, from omega t is equal to 0 to pi, Vs is positive. Pi to 2 pi, Vs is negative. 2 pi to 3 pi, again Vs is positive, right? So in the Vs we are having a positive values, negative values, positive values, and negative values. Okay, so suppose when Vs is positive, it is like a polarity is plus here and minus here. Similarly, when Vs negative, at that time these polarities should be reversed. Okay, so when Vs is positive, it is like this is the highest potential point, this is the lowest potential point. Okay, so highest potential is appearing at the anode of thyristor, lowest potential is appearing at the cathode of thyristor. So now anode is at higher potential than that of the cathode. So can we say that yes, when Vs is positive, thyristor T will be in a forward bias mode. Okay, so let me write, when Vs is positive, when Vs is positive, that is during omega t is equal to 0 to pi, right? Omega t is equal to 0 to pi, right? So Vs is positive. So therefore, what about thyristor T? Thyristor T will be in a forward bias mode. Forward bias mode. Okay. Next, similarly, when Vs is negative, what will happen? Supply voltage polarity will be reversed, na? Right? So it is like here it is minus, here it is plus. So it is like a highest, lowest potential point. Here it is the highest potential point. Lowest potential is appearing here. That is the anode of a thyristor. Highest potential through the load will appear at the cathode of a thyristor. So here can we say that cathode potential will be more than that of the anode. So thyristor T will be in a reverse bias mode, right? So let me write, when Vs is negative, it is like during omega t is equal to pi to 2 pi, right? Omega t is equal to pi to 2 pi. So thyristor T will be in a reverse bias mode. Reverse bias mode. Okay. Now, if we recall from the static VI characteristics of the SCR, okay, in the static VI characteristics of the SCR, we discussed the SCR is having the three modes. One is the forward blocking, second one is the forward conduction, and third one is the reverse blocking. Okay, so when SCR is in a forward bias mode, we are having the two modes. One is the forward blocking and second one is the forward conduction. Whereas when SCR is in a reverse bias mode, we are having only one mode of operation, that is the reverse blocking. Are you getting the point, right? So here, please try to understand, during 0 to pi, when Vs is positive, that is when thyristor is in a forward bias mode. Okay, unless and until we apply the gate signal to the SCR, our thyristor will be in a forward blocking mode. Once we apply the gate signal, our SCR will turn on. So mode of operation will be the forward conduction mode. Okay, so please try to understand here. During 0 to pi, Vs is positive. So Vs positive means thyristor is in a forward bias mode. So when thyristor is in a forward bias mode, we can apply the gate pulse to the thyristor. Okay, so here we can apply the gate pulse to this thyristor at any instant. Okay, at any instant between omega t is 0 to pi. Between 0 to pi, at any instant we can apply the gate signal. As soon as we apply the gate signal, our thyristor will turn on immediately. Are you getting the point? Okay, so next you can check when Vs is negative, it is like thyristor is in a reverse bias mode now. So when thyristor is in a reverse bias mode, and if I circulate the positive gate current in the gate cathode circuit, whether our thyristor will turn on? No, thyristor will not turn on. Okay, by circulating the negative gate current. Okay, so that's why here you can check when Vs is negative, thyristor is in a reverse bias mode. So we have not applied the gate pulse to the thyristor. We have applied the gate pulse only when Vs is in a forward bias mode. Okay, that is between 0 to pi. Similarly, you can check from 2 pi to 3 pi. Again, Vs is positive, thyristor will be in a forward bias mode. We can turn it on by applying the gate signal, right? So please keep it in mind. We are applying the gate signal only when thyristor is in a forward bias mode. That is when Vs is positive. I can apply the gate signal either at this omega t 0, at this instant, at this instant, at this instant. Any instant we can apply the gate signal to the thyristor. Are you getting the point? Right? Next. So now let us discuss the circuit operation. So suppose for omega t is equal to 0 to alpha, what will happen? Let us discuss, right? So for omega t is equal to 0 to alpha, so you can check here, omega t 0 to alpha is like, alpha means this point here. Okay, so here it is alpha. So you can check between omega t is between 0 to alpha. What is Vs? Vs is positive only. Okay, so when Vs is positive, it is like thyristor T will be in a forward bias mode. Okay, but between 0 to alpha, whether we have applied the gate signal, we have not applied the gate signal. At alpha, we are going to apply the gate signal. Okay, but between 0 to alpha, what is happening? Vs is positive, thyristor T is in a forward bias mode, but we have not applied the gate signal. Okay, so thyristor is in a forward bias mode, but we have not applied the gate signal. The meaning is thyristor will be in a forward blocking mode. Are you getting the point? Thyristor will be in a forward blocking mode. Okay, so in a forward blocking mode, we discussed during forward blocking mode, SCR is characterized with a high voltage and less current. That is a high impedance. Okay, so now during 0 to alpha, can we draw the equivalent circuit? Yes, we can draw, and we need to replace this thyristor with a open circuit, right? Thyristor with the open circuit. So between 0 to alpha, the equivalent circuit will be like this. Thyristor is in a forward bias mode, but it is in an off state because we have not applied the gate signal. So equivalent circuit will be like this. This is the Vs plus minus. Vs is positive, so polarity will be upper terminal plus, lower will be minus. This is plus minus Vt. Here it is R, V0, I0, right? This current is a IT, this current is a IS, right? Now you can check here, thyristor is in a forward blocking mode, right? Let me write here. Yes, thyristor T will be in a forward blocking mode, right? Forward blocking mode. Forward blocking mode means it is in a off state only. Okay. Next, whether the current will flow in the circuit? No, current will not flow. So let me write it as current I0 is equal to IT is equal to IS. All will be 0 ampere only. Okay. Current in the circuit is 0. So if I0 is 0, what about the V0? V0 is equal to I0 into R. V0 is equal to I0 into R. So it is equal to 0 volt. Okay. So load voltage is 0. Load current is also 0. Next, can we apply KVL to this loop? Yes, we can. KVL to loop. So we'll be getting it as a plus Vs minus Vt minus V0 is equal to 0. In that, what is the V0? V0 is 0, na? So if we replace V0 with 0, so can we get it as, let me write here. Therefore, Vt is equal to Vs. Be careful here. Vt is equal to Vs means voltage across thyristor is positive. Voltage across thyristor is a positive. Is this clear? Vt is equal to Vs means voltage across thyristor is a positive. Okay. So you can check here during 0 to alpha, Vt is same as that of the supply voltage. I0 is 0 ampere, V0 is 0 ampere, right? So 0 to alpha you can check. V0, I0 both are 0. And what about Vt? Vt is the same as that of the supply voltage. It is same as that of the supply voltage. Supply voltage is like this positive, so here it is also positive, right? Next, at alpha we are going to apply the gate pulse to thyristor. So as soon as we apply the gate pulse to thyristor, our thyristor will turn on. Once thyristor turns on, current starts flowing from source towards the load. Okay. So from alpha till pi, can we draw the equivalent circuit? Yes, for omega t is equal to alpha to pi. We can draw the circuit. It will be like yes, Vs here plus minus. This is Vt. This is It. Here it is Is. Register R, V0 and I0. So what is the mode of operation of this thyristor during alpha to pi? Come on. Mode of operation of a thyristor during alpha to pi. Yes. During alpha to pi, the mode of operation of thyristor. On state, okay, on state is fine, but I'm asking the mode of operation. Yes, forward conduction. Good, good, good. Mode of operation means, because sometimes they have asked the question, okay, during alpha to pi, the thyristor will be in which mode of operation? Mode of operations we specified in, yes, static wave characteristics. Na? So it is a forward conduction mode. Thyristor is in a forward bias mode, and we have applied the gate signal. So it will be in a conduction mode. So forward conduction mode, right? So thyristor T will be in a forward conduction mode. So let me write here. Thyristor T will be in a forward conduction mode. Forward conduction mode. Previously it was in a forward blocking mode. Now it is in a forward conduction mode. Okay. So if forward conduction mode, so Vt is equal to 0 volt. Vt is equal to 0 volt, right? Voltage across thyristor will be 0. Okay. If we consider this thyristor as an ideal switch, then it will be 0. Okay. If they give that on-state voltage drop, suppose if they give the on-state voltage drop of the thyristor is 2 volt or 1.5 volt, then we need to consider that voltage here. Okay. So next, so Vt is 0 volt. Now can we apply KVL to this loop? Yes, KVL to loop. So we can write it as plus Vs minus Vt minus V0 is equal to 0. Out of that, Vt is 0. So therefore V0 is equal to same as that of the supply voltage. V0 is equal to Vs, right? Next, so V0 is Vs, Vt is 0. What about the I0? According to Ohm's law, I0 is equal to V0 by R, or V0 is equal to I0 into R. Okay. So therefore I0 is equal to V0 by R, which is equal to Vs by R. Again, whether I0, It and Is all will be same or different, all will be same. Na? We are having only one loop, right? So let me write also Is is equal to It is equal to I0, which is equal to Vs by R only, right? Which is equal to Vs by R only, right? So here you can check during alpha to pi, Vt is 0, V0 is same as that of the supply voltage, I0 is equal to V0 by R. Okay, means you can check I0 and V0 will be in phase only because load is a purely resistive. Okay, as if V0 increases, I0 also increase. V0 decreases, I0 will decrease. Okay, so you can check the waveform. Alpha to pi, V0 is same as that of the supply voltage. I0 will be, yes, nature will be same. The only thing is the change in the magnitude. Okay, next, alpha to pi, Vt is a 0. Vt is equal to 0, right? Next, now you can check here. At omega t is equal to pi, at omega t is equal to pi, the supply voltage becomes 0. Okay, so if supply voltage becomes 0, so what about the load voltage? Load voltage is also becoming 0. Load current is also reaching the 0 value at omega t is equal to pi. So at omega t is equal to pi, load current is 0. So can we say that the thyristor current also 0? Yes. At omega t is equal to pi, thyristor current is 0 means first condition for commutation of thyristor has reached. Yes or no? For the commutation of thyristor, we are having the two-step procedure. One is, first of all, anode current of the thyristor should be less than the holding current value. And at omega t is equal to pi, due to the nature of the source, it is reaching the zero, now I0 is reaching to the 0 ampere, means I0 means definitely your IT is also equal to 0, right? So IT is reaching the 0 value at omega t is equal to pi, right? So first condition for commutation has reached, right? What is the second requirement? The second requirement, we need to maintain the reverse voltage. Now we can check from pi to 2 pi what will happen in the circuit, and then you will understand how the reverse voltage, yes, will be maintained across the thyristor. So from pi to 2 pi, you can check supply voltage is negative. So when supply voltage is negative, the polarity will be reversed. Okay. So when polarity is reversed, it is like thyristor will be in a reverse bias mode now. So it is like thyristor in a reverse bias mode, we are having only one mode of operation, that is the reverse blocking mode. Okay. So from pi to 2 pi, can we say that our thyristor will be in a reverse blocking mode only, right? So let me draw the circuit for omega t is equal to pi to 2 pi. For omega t is equal to pi to 2 pi. Yes. Circuit will be like this. Supply voltage Vs. Thyristor is in off state. At omega t is equal to pi only, thyristor T will turn off. It means it will act as an open circuit. And but whether it will be successfully commutate or not, it depends on your reverse voltage. Okay. For successful commutation, the condition is TC should be greater than or equal to TQ, na? Right? Yes. So this is a Vs. Polarity is minus here, plus here. Okay. This is Is. This current is IT. This voltage is Vt. R. V0. And here it is a I0. Right? Now you can check here. Supply voltage is reversed, negative. Okay. Thyristor will be in a reverse blocking mode. Thyristor T will be in a reverse blocking mode. Reverse blocking. Is this clear? Right? Next. So now during this mode, thyristor is acting as an open circuit or the open switch. So what is the I0? I0 0. So let me write Is is equal to IT is equal to I0. All will be equal to 0 ampere only. What is the V0? V0 is equal to I0 into R, which is equal to 0 volt. Okay. V0 is 0 volt. I0 is also 0. Next, what about the Vt? For finding the Vt, we can apply KVL to the loop. Okay. So KVL to loop. So we can write it as minus Vs. Okay. Plus to minus, so minus Vs. Plus minus Vt. Plus minus V0 is equal to 0. In that V0 is 0, na? We have written V0 is 0. So therefore, Vt is equal to minus Vs. Be careful. Here Vt is a negative voltage. Vt is a negative voltage. Okay. So from pi to 2 pi, you can check the waveform. Current is 0. Load voltage is 0 volt. And thyristor voltage is negative voltage. Right? Next. So here you can check from pi to 2 pi. From pi till 2 pi. This is a 2 pi. V0, I0 both are 0. And what is the Vt? Vt is a negative. And it is having same as that of the supply voltage. Okay. Due to the lack of space, actually I have drawn this type of shape. But strictly speaking, this pi to 2 pi, this wave shape and this supply voltage wave shape both should be same. Okay. So it is like your minus Vs only. Okay. That is same as that of the supply voltage. Next. So this is the circuit operation. Now you can check here. Corresponding to one input cycle in the output, how many pulses we are getting? We are getting only one pulse, na? From 0 till 2 pi. From 0 till 2 pi, supply is completing one cycle. Corresponding to that one cycle in the output, we are getting only one pulse. We are getting only one pulse. So that's why it is also known as a single phase, single pulse. Okay. Controlled rectifier. Single phase, single pulse, controlled rectifier. Let me write. Yes. This circuitry is also known as single phase, single pulse controlled rectifier. So if the input supply frequency is 50 Hertz, then what about the output pulse frequency? If the input supply frequency is 50 Hertz, then what will be the output pulse frequency in this case? Come on. same, right? Same. Whatever we discussed in the yesterday session, same here, right? So if the input supply frequency is 50 hertz, therefore we'll be getting in the output 50 pulses na, corresponding to 1 second. So that's what the same frequency. So let me write output pulse frequency. Output pulse frequency is equal to input supply frequency. Input supply frequency. Input supply frequency. Next, whether the output, whatever we are getting, is a flat DC. No, it is not a flat DC. So it is a pulsating DC. Okay, it is a pulsating DC. Is this clear? Right? Next. So now we are going to derive the expressions. Okay, just like a V0 average, I0 average, V0 RMS, I0 RMS, conduction time of thyristor, circuit turn off time of thyristor, input power factor, PIV rating, etc. Okay, so let us derive one by one. Average output voltage. Average output voltage. So that is the V0 average is equal to, yes. So here what is the periodic angle of the V0? What is the periodic angle of V0? You can check from 0 to 2 pi, whatever the waveform we are having, the same will repeat from 2 pi to 4 pi. Na? So periodic angle is a 2 pi. So that's why it is a 1 by 2 pi. Let me write it as a 1 by 2 pi. Integration from, this is the average, na? Right? So we need to integrate the instantaneous values. We need to add the instantaneous values. Integrate means adding. Now you can check between 0 to 2 pi, we are having 3 sub intervals like 0 to alpha, alpha to pi, and pi to 2 pi, na? Right? But in that you can check 0 to alpha, what is V0? 0. So what is that integration of 0? 0 only. Alpha to pi, V0 is same as that of the supply voltage, na? V0 will be same as that of the supply voltage. And pi to 2 pi, V0 is again 0. Okay. So what is the integration of that 0 again? It will be 0. So the effective interval out of the 0 to 2 pi, we are having the 3 intervals, 0 to alpha, alpha to pi, and pi to 2 pi. In out of these 3 intervals, the effective interval will be like alpha to pi only, na? Right? So instead of writing that 0 to 2 pi, if I write directly alpha to pi, okay, and it is a V0 into d omega t, that will be same, na? Are you getting the point? Okay, means instead of writing 0 to 2 pi, and in the next step, that 0 to 2 pi can be divided 0 to alpha, alpha to pi, and pi to 2 pi. Okay, and again we are going to put that 0 to alpha, it is a 0 and those things. Okay, so I am directly putting the effective interval. Is this clear? Right? So it is equal to 1 by 2 pi integration from alpha to pi. What is the V0 during alpha to pi? It is the same as that of the supply voltage. So it is a Vm into sine of omega t into d omega t. Right? Can we take this Vm outside? Yes, it is a constant. So it is a Vm by 2 pi into integration of sine is minus cos of omega t, limit alpha to pi. So we can write it as is equal to Vm by 2 pi into, if we put the limit, it will be like a 1 plus cos alpha. Okay, so this is your V0 average. V0 average is equal to 1 Vm by 2 pi into 1 plus cos alpha. Okay, now you can check here, average output voltage varies with firing angle alpha. Right? Now what is the firing angle alpha? Let us discuss. Okay, so firing angle means what? It is the instant at which, okay, we apply the triggering pulses to the SCR. Okay, that is nothing but the firing instant. And the firing angle means it is the angle measured from, the instant at which or after which the thyristor becomes forward bias. Okay, the instant after which the thyristor becomes forward bias. Okay, from this instant till the instant at which apply the gate signal to the thyristor, that corresponding angle is nothing but your firing angle. So firing angle is measured from the instant at which thyristor becomes the forward bias. Okay, thyristor becomes the, or thyristor, yes, thyristor will be in a forward bias mode. Okay, so you can check after omega t is equal to pi, Vs is positive, so thyristor will be in a forward bias mode. Okay, and at alpha we are applying the gate pulse or the triggering pulse. So that's why this indicates your firing angle alpha. 0 to alpha means this is alpha only, na? Okay, so this is the firing angle alpha, right? Now, yes, V0 average expression we are having Vm by 2 pi into 1 plus cos alpha. So if I change the alpha, that is if I vary the alpha, whether the average output voltage will vary, definitely the average output voltage will vary. That's why it is known as the controlled output. That's why it is known as a controlled converter. Are you getting the point, right? Whereas if you check with a diode rectifier in the yesterday session, whatever we discussed, in that case there was no alpha, na, right? And what was the expression? The expression for V0 average was like only Vm by pi. Okay, means for the fixed input we are getting the fixed output, but here for the fixed input we can get the variable output, right? Variable output means we can get the average value of the output voltage, okay, any value, right, as per our requirement, right? So by keeping the value, by changing the value of alpha, that's why it is known as the controlled rectifier, controlled converter. Yes or no, right? So this is the V0 average, Vm by 2 pi into 1 plus cos alpha. No need to memorize the expression. The only thing is please try to understand how to derive the expression, right? In power electronics, the thing is you need to practice the circuit diagram. Once you understand the circuit diagram, once you memorize the circuit diagram, after that you can draw the waveform from the circuit operation, right? And from these waveforms you can derive the expression. Okay, yes, you need to do the practice first. Next, so this is the V0 average. Now average output current, I0 average output current, that is the I0 average. Yes, it is equal to V0 average by R. So it is equal to Vm by 2 pi R into 1 plus cos alpha. 1 plus cos alpha. This is your I0 average, right? Average value of output current or the load current. Okay. So next, RMS output voltage. RMS output voltage. RMS output voltage. Yes. V0 RMS. Square root of mean of squared value. Okay. So in the same way, whatever we how we calculated in the yesterday's session, it is like 1 by 2 pi integration from alpha to pi Vm square into sine square of omega t into d omega t, right? Square root of mean of squared value. We are taking here mean of the squared value. So instead of Vm sine omega t, now it should be Vm square sine square of omega t. Okay, means instead of V0, now here it should be V0 square, na, right? So we need to simplify it. It is like a Vm upon, I'm taking this Vm square outside, divided by 2 pi also outside. So it is like Vm upon root 2 pi into, we can write this as integration from alpha to pi. Sine square of omega t can be replaced with 1 minus cos of 2 omega t divided by 2 into d omega t to the power 1 by 2, right? So it is equal to this divided by 2 also we can take outside. So it is like Vm upon 2 root pi into, this can be written as omega t minus integration of cos is sine of 2 omega t divided by 2 limit alpha to pi to the power 1 by 2, right? Next, put the limits. So we'll be getting, it is like V0 RMS. Therefore, V0 RMS is equal to, yes, so is equal to pi minus alpha. Yes, Vm by 2 root pi, Vm upon 2 root pi into pi minus alpha minus sine of 2 pi by 2 plus sine of 2 alpha by 2. Okay, minus sine of 2 pi by 2 plus sine of 2 alpha by 2. Okay, to the power 1 by 2. What is the sine 2 pi? That is the sine 360. Okay, it is a 0. So only sine 2 alpha by 2 will be there. So therefore V0 RMS is equal to Vm upon 2 root pi into bracket pi minus alpha plus sine of 2 alpha divided by 2 to the power 1 by 2. This is the V0 RMS value of output voltage, right? Next, I0 RMS, which is equal to V0 RMS divided by R. Load is a purely resistive, okay? So V0 RMS divided by R, right? Next, what is the load power? Load power, or you can say output power also, okay? Yes, P0 average is equal to, we discussed in the yesterday's session, okay? P0 average at left hand side, yes, we're having the average, but at the right hand side, we'll be having the product of na RMS voltage and RMS current, okay? So V0 RMS into I0 RMS, which is equal to V0 RMS square divided by R, which is equal to I0 RMS square into R, right? All these three are the valid expressions for average output power or the load power, okay? P0 average. Next, conduction time of thyristor. Conduction time of thyristor, yes. Yes, can anyone? What is the conduction time of thyristor? Conduction time of thyristor. Thyristor will be in a on state from alpha till which instant? Alpha till which instant? Till pi na? You can check Vt is 0 na, from alpha to pi. So from alpha to pi, thyristor T is in a on state na. That is a forward conduction mode. So what is the conduction angle? Conduction angle is pi minus alpha. So conduction time pi minus alpha by omega, right? Pi minus alpha by omega, right? Yes, pi minus alpha by omega. So let me write here, which is equal to pi minus alpha divided by omega. This is the conduction time of thyristor. Next, what is the PIV rating of thyristor? PIV rating of thyristor. Yes, for that you can check the Vt waveform. What is the peak value of reverse voltage across the thyristor? Yes, it is the same as that of the peak value of the supply na? So this is the V max, yes or no? So what is the PIV? It is a VM, right? It is a VM. You getting the point? Right, it is a VM. Don't write the minus VM. Huh? I'm repeating it. Yesterday also I told you the same thing, because here the inverse word is there, okay, in the PIV. So that's why I want to write only the magnitude. That is the VM, right? Next, what is the circuit turn off time for thyristor? Circuit turn off time. Circuit turn off time. That is a TC for thyristor. For thyristor. Yes, how to find the circuit turn off time for thyristor? The first thing is we need to identify the instant at which current flowing through thyristor becomes 0. And after that, we need to measure the time till which the reverse voltage is maintained, okay, across the SCR or across the thyristor. So at which instant the current flowing through thyristor becomes 0? At which instant the current flowing through thyristor becomes 0? Come on. Current flowing through thyristor becomes 0 at pi, right? At omega t is equal to pi, current flowing through thyristor becomes 0, right? Same thing we discussed, because at pi, I0 and IT both will be 0, no? Right? So at pi, current flowing through thyristor becomes 0. And after pi, you can check the reverse voltage will be maintained across thyristor, no? Reverse voltage we need to check. Reverse voltage is maintained from pi till 2 pi, na? After 2 pi, whether it is a reverse voltage? No. After 2 pi till 2 pi plus alpha, it is a positive voltage, that is a forward voltage. We require only the reverse voltage, na? So you can check current flowing through thyristor becomes 0 at omega t is equal to pi, and after that the reverse voltage will be maintained till 2 pi. So what is the circuit turn of time? Circuit turn of time is a time corresponding to this reverse voltage, that is a TC, 2 pi minus pi divided by omega. Is this clear? 2 pi minus pi by omega, which is equal to pi by omega, right? Which is equal to pi by omega. Next, what is the input power factor? Input power factor or the supply power factor. Input power factor, which is equal to supply power factor. Supply power factor. Yes. How to find the input power factor? Yesterday we discussed this thing. In the circuit, if you check, we are having only source, thyristor, and it is a load now. And what about the power loss in this thyristor? This is the ideal thyristor, so power loss will be 0. So only thing is whatever the power supplied by the source is equal to power absorbed by the load, power consumed by the load. Yes or no? Right? So here we can write it as a source power. Source power is equal to load power, or you can write power supplied by the source is equal to power consumed by the load. Okay. Source power is equal to load power. What is the source power? Vs RMS into Is RMS into cos phi s, which is equal to load power. Load power is a P0 average. Are you getting the point? Okay. So therefore we can write cos phi s. P0 average. P0 average is V0 RMS into I0 RMS, right? V0 RMS into I0 RMS divided by this Vs RMS into Is RMS. Okay. So whether I0 RMS and Is RMS both will be same or different? Come on, speak out. Whether V0 RMS and I0 RMS both will be same or different? Same, right? Both will be same, correct? So I0 RMS and Is, you can check the waveform. Okay, circuit operation during 0 to alpha, both are 0. I0 and Is both are 0 because thyristor is in off state. Alpha to pi, thyristor is acting as a short circuit, conduction mode. Okay, so Is and I0 again both are same. And from pi to 2 pi, thyristor is in off state. Okay, so again it will be 0, right? So both are 0. So we can write it as, which is equal to V0 RMS divided by Vs RMS. This is the expression for cos phi s. Okay, either here you can replace this V0 RMS with the expression. Okay, whatever we derived for the V0 RMS expression, you can write this expression there or keep it as it is. It doesn't matter. Okay, but important thing here is, here you can check V0 RMS will be in terms of alpha now. V0 RMS will be in terms of alpha. So your input power factor depends on the value of firing angle alpha, value of firing angle alpha. But whereas if you check in the diode rectifier, whatever we discussed in the yesterday session, okay. So in that case, there was we didn't have the term like alpha na firing angle. So there, whatever the whatever the input power factor, that was the constant actually there. But here it depends on the alpha because your V0 RMS varies with the alpha here, right? Next. So this is about the circuit operation of single phase half wave controlled rectifier with a purely resistive load, right? So simple circuit. Now let us discuss for purely inductive load what will happen. Okay, purely inductive load. Single phase half wave controlled rectifier with purely inductive load, L load. Vs thyristor T, this is Vt, It, Is, L, V0, I0, right? So waveforms. Yes. Vs is Vm sin omega t. Suppose this is a gate pulse we applied. Alpha 2 pi plus alpha, right? Next, V0 and I0. Alpha pi beta 2 pi 2 pi plus alpha and 3 pi. Okay, so I0. Right, I0. So it will be slowly increasing, reaching to the peak value and again decreasing, right? We'll discuss. Yes. So single phase half wave controlled rectifier with purely inductive load, right? With purely inductive load.
Hello, sir.
Do you want to say something?
Yes, sir.
Sir,
good evening. Sir, I said that explain after sir, after explaining, draw the diagram actually. Otherwise, it is the pictorial already view in our mind that the graph will be like this. So it is actually
okay, I will try. Okay, I will try. Okay.
means not okay. Okay.
ठीक है, ठीक है, ठीक है. Yes. So single phase half wave control rectifier with purely inductive load. So same circuit diagram we are having, and here we are having a load is a purely inductive. So Vs is Vm sin omega t, right? Vm into sin of omega t. 0 to pi Vs is positive, pi to 2 pi Vs is negative, 2 pi to 3 pi Vs is again positive. Okay, so when Vs is positive, we know thyristor will be in a forward bias mode, so we can apply the gate pulse. So at alpha we have applied the gate pulse. You can check alpha is between 0 and pi na. Next, when Vs is negative, we have not applied the gate signal, right? So how the circuit operates, we'll discuss. 2 pi to 3 pi Vs is positive again here. Okay, so again we are going to apply the gate pulse. So now from omega t is equal to 0 to alpha, for omega t is equal to 0 to alpha, yes, it is like a Vs is positive, but we have not applied the gate signal to the thyristor. So how will the circuit diagram for the omega t is equal to 0 to alpha, right? So for omega t is equal to 0 to alpha, yes, the circuit will be like this. Thyristor is in a forward bias mode, but we have not applied the gate signal. Okay, So mode of operation will be forward blocking mode, right? So this is the L, this is the V0, and here it is a I0. This voltage is VT, na? And here it is a current IT, IS, right? IS. Same. So here IT, I0, IS all will be 0. I0 is equal to IT is equal to IS is equal to 0 ampere, right? Next, what about the V0? V0 is equal to 0 because voltage across inductor is L into di by dt. Na? That is, in this case, it is L into di 0 by dt. But from 0 till alpha, where current is 0 only. So what is the di 0? Change in the current will be 0, right? So that's why V0 will be 0. What is VT? If we apply KVL to the loop, we'll be getting KVL to loop. So it is like a plus Vs minus Vt minus V0 is equal to 0. V0 is equal to 0. So therefore Vt is same as that of the supply voltage. So you can check from, yes, Vt waveform we have not drawn here, but we can draw at the end. I will draw. Okay. So because the lack of space, yes, we will draw the Vt waveform at the end. So you can check for omega t is equal to 0 to alpha, V0 0, I0 0. Okay. So V0 is 0, I0 is also equal to 0, right? This is till alpha. At alpha, we are going to apply the gate pulse. So what will happen? Once gate pulse is applied, our, yes, thyristor starts conduction. Current will flow from Vs, thyristor load, and again back to the Vs. In this loop, the current will be flowing. Yes or no? Right? So let me draw the circuit for omega t is equal to alpha to pi. For omega t is equal to alpha to pi. For omega t is equal to alpha to pi. Yes. Circuit will be like this. Thyristor will be in a forward conduction mode now. Forward conduction mode. This is a Vs plus minus. This is a Vt, It, Is, right? L, V0, and here it is I0, right? So now you can check here. Yes, once thyristor is in a conduction mode, so what is a Vt? Vt is equal to 0 volt, right? When Vt is 0 volt, and if we apply the KVL, we'll be getting V0 is equal to Vs. You can apply KVL, you can check. V0 is equal to Vs volt. Okay. What about the I0 nature? I0 will be increasing slowly, na? Right? Okay. Because we're having the inductor. Inductor opposes the sudden change in the current. Okay. So before omega t is equal to alpha, if you check the current flow through the inductor was 0. So after alpha, yes, the nature of the inductor current will be increasing slowly. And you can check the V0 waveform. At alpha, before alpha, V0 was 0. At alpha, once thyristor turns on, V0 becomes equal to Vs. So at alpha, if you check the Vs value, at alpha, what is the Vs value? Vs value is this one. Na? This value of Vs is nothing but Vm into sine of alpha. Na? At omega t is alpha. This is alpha. Na? Omega t is equal to alpha. Vs is equal to Vm sine alpha. So that's why V0 will suddenly increase from 0 to the Vm sine alpha. And after that, it is having the same wave shape as that of the supply voltage. Now, yes, during this interval, can we find the expression of the current I0? Yes, we can find. Okay. How to find the expression of the current I0? Let us discuss. Okay. So you can check V0 we're having, which is equal to Vs, but V0 is equal to Vs. V0 means what? L into di0 by dt. Na? So let me write V0 is equal to Vs, and V0 is nothing but L into di0 by dt, which is equal to Vs. What is a Vs? Vm sine omega t. Na? So it is a Vm into sine of omega t. Right? Further, we can write it as di0 is equal to Vm upon L into sine of omega t into dt. I have shifted this dt to right hand side, this L to the right hand side. Okay. So can we take the integration on both the sides? Yes, integrating both sides. So what will happen if you take the integration both the sides? integration of di0 is equal to integration of Vm by L into sine of omega t into dt plus integration constant c. Okay. Now, yes, we can write it as a integration of di0 is I0, which is equal to Vm by L is a constant, so we are taking outside. Integration of sine of omega t, it is a minus cos of omega t divided by omega, na? Because integration is with respect to time. Okay, so that's why divided by omega, and plus this c will be there. So we can write this as I0. Let me write I0 is equal to, yes, Vm by omega L or minus Vm upon omega L into cos of omega t plus c. Okay, consider it as equation 1. Now we need to find the value of c, right? Constant c by using the initial condition. Okay, so what is the initial condition? You can check. This interval is from alpha to pi. So at the instant of alpha, at omega t is equal to alpha, what will be the value of I0? At omega t is equal to alpha, what will be the value of I0? Yes, can anyone? At omega t is equal to alpha, what will be the value of I0? Yes, I0 is equal to 0 only, na? Because before omega t is equal to alpha, it was like a thyristor was in off state, inductor current was 0. So even though at alpha switch is closed, thyristor is acting as a short circuit, but our inductor will act as an open circuit at alpha, right? So we can write at omega t is equal to alpha, I0 is equal to 0 ampere. I0 is equal to 0 ampere, right? Now we need to put these two in equation 1. Okay, so from 1, replace omega t with alpha and I0 with 0. Okay, so 0 is equal to minus Vm upon omega L into cos of alpha, right? Plus this is c. Okay, I will replace this I0 with 0, omega t with alpha. So therefore c is equal to Vm upon omega L into cos alpha. This is the c. Further, we need to put this c in equation 1. Okay, put this c in equation 1. Okay, so put this c in equation 1. Okay, so therefore I0 is equal to minus Vm upon omega L into cos of omega t plus Vm upon omega L. This term I am putting here. Okay, into cos of alpha. So further we can write therefore I0 is equal to Vm by omega L. This Vm by omega L, here it is also Vm by omega L. So I'm taking it common. Okay, into cos of alpha minus cos of omega t. This is the expression for current in the circuit. Okay, expression for current in the circuit, right? Vm by omega L into cos of alpha minus cos of omega t. Now you can check here. At omega t is equal to alpha, if you put here omega t is equal to alpha, it is like cos alpha minus cos alpha. So this term will, this bracket will become 0. So I0 will be 0, right? After that, as omega t increases, cos alpha is fixed, na, because alpha means firing angle. So this cos alpha value will be fixed. Okay. So as omega t increases, right? Suppose after alpha, we are increasing the omega t. Okay. Omega t is increasing means it is like this. Omega t increasing. This is at omega t is alpha. After that, as omega t increases, yes, as omega t increases, what about the cos alpha value? What about the cos of omega t value? Will be decreasing, na? Because omega t, I am saying that, yes, omega t increases means now your omega t is greater than alpha. Okay, so as the angle increases, yes, and if the angle is greater than alpha, therefore this term will go on decreasing. As this term decreases, yes, it is like your cos alpha minus this term, the difference go on increasing. Difference increases means I0 increases. Is this clear? right? So let me write here. Yes, for or at omega t is equal to alpha, at omega t is equal to alpha. Yes, it is I0 is equal to 0 ampere. Okay. Next, at omega t, let us consider it as a pi by 2. Omega t is a pi by 2. Okay, so if it is a pi by 2, so it is a cos of pi by 2. What is cos pi by 2? 0 na? So it is like Vm by omega L into cos alpha. Vm by omega L into cos alpha. I0 is equal to Vm by omega L into cos of alpha, right? Next, at omega t is equal to pi. At omega t is equal to pi. What is I0? You can check here. Cos of alpha minus cos of pi. Cos pi is -1. Na? So cos alpha minus of -1. So it is like a 1 plus cos alpha. This term will be, this bracket will be. Okay. So I0 will be Vm by omega L into 1 plus cos alpha. Okay. So it is Vm by omega L into 1 plus cos alpha, right? Vm by omega L into 1 plus cos alpha, right? So you can check here from alpha till pi, your I0 is increasing only. I0 is increasing only. So that's why here if you check the I0 waveform, yes, I0 waveform from alpha till pi, it is reaching at pi, it is reaching a peak value. After pi, what will happen? We are going to discuss, right? But is this clear? From alpha to pi, it is like inductor is just storing the energy, na? Because your V0 means voltage across inductor. It is same as that of the supply voltage. So V0 is a positive. You can check V0 waveform from alpha to pi. V0 is a positive, na? Same as that of the supply voltage, it is a positive. So V0 positive means what? V0 is nothing but the voltage across inductor now in this case. So voltage across inductor is positive. The meaning is L, your di0 by dt, right, is a positive because voltage across inductor is L into di0 by dt. So V0 is positive means di0 by dt is positive. So your di0 by dt is positive means slope of the current will be like this, and your inductor is storing the energy. Inductor is storing the energy. So till pi, inductor stores the energy. That's why current is at its peak value. Current is at its peak value. Next, after pi, what will happen? After pi, what will happen? Let us discuss. So from pi till beta, from omega t is equal to pi till beta. Let me write here. For omega t is equal to pi to beta. Omega t is equal to pi to beta. Yes, it is like supply voltage is negative now. It will reverse its polarity. But inductor will oppose the sudden change in the current, now sudden reversal of the current through it, right? So supply voltage will be minus here, plus here. This is the V0. Here we are having the L. This is a VT. Here it is a IT. Here it is a IS. Okay. And this current is a I0. So here inductor is releasing the energy now. Inductor is releasing the energy. Yes or no? Right? So inductor is releasing the energy. So now you can check this circuit and this circuit, whether both are same or different. You can check here also thyristor is in on state. Here also thyristor is in a on state. Yes or no? Thyristor is in a on state. Right? So in the same way, whatever we discussed just now, in the same way we can apply the KVL and we can simplify it. Okay. And at the end, what you will understand, at the end, what we will be getting is very interesting, because after this, what is happening? Your V0 is a negative, right? V0 is a negative. You can apply KVL. VT is a 0, right? VT is equal to 0 volt. Next, apply KVL to loop. KVL to loop, it is like a minus Vs minus Vt minus V0 is equal to 0. Okay. Out of that, Vt is 0. So therefore V0 is equal to minus Vs, right? Load voltage is equal to negative here. Load voltage is a negative. Now load voltage means what? It is a voltage across inductor only, na? This V0 is nothing but voltage across inductor only. Voltage across inductor. And what is the voltage across inductor? It is a L into di0 by dt, which is equal to minus Vs. So now from this, can we write di0 by dt will be negative? Yes. So di0 by dt will be negative. So what this term indicates, di0 by dt negative, it indicates that inductor is releasing the energy, right? Inductor is releasing the energy. So as di0 by dt is a negative, so it indicates that inductor releases energy, right? So till which instant inductor will release the energy? Till which instant the inductor will release the energy? Yes, here it is. Till beta, till omega t is equal to beta, inductor will release the energy. Now you can check in the previous case, in the yesterday session, whatever we discussed, in that case we had a diode, okay, and in that case we discussed that during 0 to pi inductor was storing the energy, and from pi to 2 pi inductor was releasing the energy. Okay, so always keep it in mind. If the load is purely inductive, in the case of that load, whatever the time for which the inductor has stored the energy, the time for which inductor has stored the energy is always equals to the time for which the inductor will release the energy. Means if the load is purely inductive, this is valid, this is applicable only for the purely inductive load. Okay, because you can check in this circuit, whether whether we are having the any other element which can absorb the energy. We are having only inductor, we don't have the resistor here, passive element, okay, which can absorb the energy, right, which can absorb the power. Only inductor we are having. So what is the thing here? Inductor is storing the energy and inductor is releasing the energy. And in the case of purely inductive load, keep it in mind, the time taken by the inductor to store the energy is always equals to the time for which the inductor releases the energy. The meaning is in the previous case it was like from 0 to pi inductor was storing the energy. So during which angle, corresponding how much angle inductor was storing the energy, in the yesterday session we discussed 0 to pi means during pi radian inductor was storing the energy. So after pi, if you check the carefully, after pi inductor was releasing the energy for next pi radian. So from pi till 2 pi, pi to 2 pi means total difference is 2 pi minus pi, means it is again pi radian. Means inductor was storing the energy for pi radian, and again for next pi radian inductor was releasing the energy. Here also the same thing will happen. What is here? Inductor is storing the energy from alpha to pi, means for how much angle inductor is storing the energy? Alpha to pi means pi minus alpha. During this inductor is storing the energy, and after pi inductor will take next pi minus alpha, pi minus alpha angle to release the energy, So let me show here. This is the angle which indicates the pi minus alpha. Okay, this is the angle during which, let me write angle during which inductor storing energy. Okay, so what is this angle? This angle is a pi minus alpha. Yes or no? Which is equal to pi minus alpha. So after pi, inductor will take again pi minus alpha angle. I am saying after pi, inductor will take a pi minus alpha angle to release the energy. So if this is pi, and again if we add pi minus alpha in this is again pi minus alpha. Are you getting the point? This is pi minus alpha during which inductor is storing the energy. Here also pi minus alpha during which inductor will release the energy. So can we say that this instant, that is the beta, is nothing but this pi plus this pi minus alpha? Yes or no? Beta is equal to what? Pi plus this angle, and this angle is pi minus alpha. So it is like pi plus pi minus alpha. So it is like a 2 pi minus alpha. Are you getting the point? So beta is equal to 2 pi minus alpha. In the yesterday's class we discussed in that case alpha was 0, so that's why your pi minus alpha means what? Only pi was there. Okay, so for that means for pi radian inductor was storing the energy. So from pi, after that next pi radian inductor will be releasing the energy. So here it is, inductor will take a pi minus alpha angle more to release the energy. So beta is equal to pi plus in bracket pi minus alpha. So it is like pi plus pi, that is a 2 pi minus alpha. So beta will be your 2 pi minus alpha here. Beta will be equal to 2 pi minus alpha, right? So let me write here. Next. Yeah. For pure inductive load, yes, angle during which inductor stores energy is equal to, yes, angle for which inductor releases energy. So you can check here, energy stored is equal to energy released. Okay, so what is the angle here? It is a pi minus alpha, and this is equal to your beta minus pi. Na, we return beta minus pi. You can check, inductor is releasing the energy from pi till beta. Na? So this is like a beta minus pi. Okay, so from this we can find the beta. Okay, so therefore beta is equal to like a 2 pi minus alpha. Beta is equal to 2 pi minus alpha. But this is valid, applicable only for purely inductive load. Purely inductive load. Is this clear? Are you getting the point? Okay. Or else from this expression also you will understand, right? From this expression also you can understand. Yes, from this expression also you can understand. After pi, you can check this cos of pi will go on decreasing. Okay. So this difference will go on decreasing. So again, your I0 will be decreasing. Okay. Same way, in both the ways you can check, you will be getting the same value. Beta is equal to 2 pi minus alpha only. Beta is equal to 2 pi minus alpha only. Okay. So, right. Okay. Here means 2 pi minus alpha means you can put here cos omega t. Omega t, replace that omega t with 2 pi minus alpha. It is like cos of 2 pi minus alpha, na? So cos alpha minus cos of 2 pi minus alpha. Cos of 2 pi minus alpha means it is like a cos of minus alpha. Cos of minus alpha will be equal to cos alpha only, na? Right? Recall the cosinusoidal waveform. Cos of minus alpha is equal to cos alpha only. So cos alpha and this minus cos alpha will be getting cancelled. You will be getting I0 is 0 at omega t is equal to 2 pi minus alpha. You can check it. You will be getting, right? So this is very important, right? This is a very important, right? Next. So this will continue till your beta. After beta, what will happen? After beta, what will happen? So it is like till beta, inductor was releasing the energy. After beta, what will happen? After beta, it is like inductor has not having any energy to release now, or supply energy is greater than that of the inductor energy. So what will happen? The yes, resultant voltage will be reverse and thyristor will be in an off state. Okay, so circuit will be at a rest position. So for omega t is equal to beta to 2 pi, circuit will be at the rest position. It is like this. Vs minus plus, this is your Vt, It, Is, L, V0, I0, right? V0 and I0. Okay. So therefore here I0 is equal to 0 ampere, V0 is equal to 0 volt, right? Because current is not flowing now, right? So next, what about the Vt? Vt is equal to your minus Vs. You can apply KVL. You will be getting Vt is equal to minus Vs, right? So this will continue till 2 pi. After 2 pi, again the same cycle repeats. Okay, after 2 pi, the same cycle repeats, right? Next, what is the peak value of I0 in this case? Peak value of I0. Yes, you can check peak value of I0. Peak value of I0 means it is like this one. Okay, this indicates the peak value of I0 because at omega t is equal to pi, I0 is at its peak value, na? So it is a Vm by omega L into 1 plus cos alpha. This is the peak value of the current flowing through the circuit. Peak value of current flowing through the circuit. Okay, next. So this is the circuit operation. Let me explain it again on this circuit diagram. Okay, what is happening in the circuit? From omega t is equal to 0 to alpha, thyristor was in an off state. It is like a forward blocking mode. right? Thyristor is in off state, current will not flow from source towards the load. So your load current will be 0, I0 0, right? V0 is also equal to 0. Vt is equal to Vs. Vt is equal to Vs. At alpha, we are applying the gate pulse to the thyristor. Once the gate pulse is applied to thyristor, thyristor will turn on. Okay. So from alpha to pi, it is like a supply voltage is positive. Inductor go on storing the energy. Inductor go on storing the energy. So during alpha to pi, what is happening? V0 is equal to Vs. Vt is equal to 0. Inductor is storing the energy. So your di0 by dt will be positive. V0 is equal to Vs. This is a positive, right? After pi, what will happen? Supply voltage will be reversed. Inductor go on releasing the energy. Inductor go on releasing the energy. Okay. So when inductor releases the energy, okay. So in that, when inductor releases the energy, it is like inductor is releasing the energy in opposition to that of the supply voltage, because after pi supply voltage is negative na. So it is like minus here and plus here. Supply voltage will try to circulate current in this direction, but inductor energy is greater than that of the supply energy. Near to the pi, you can check na. Inductor energy is high. Inductor energy is equal to half into Li square na. So current is a high. So that's why your inductor energy will be more. So that's why resultant current will be flowing like this. The thyristor T will be in a conduction mode only. Okay. And inductor go on releasing the energy. So inductor is releasing the energy. So V0 is equal to your minus Vs. That is negative voltage. Same as of the supply voltage, but it is a negative. This will continue till beta. Again, important thing I told you, angle, yes, during which inductor stores the energy is equal to your angle for which inductor releases the energy. Means here pi minus alpha angle, inductor is storing the energy. So after pi, inductor will take again pi minus alpha more angle to release the energy. So from that we have calculated the beta value, and that beta value is equal to 2 pi minus alpha, right? Beta is equal to 2 pi minus alpha, right? They have asked the questions, right? So please try to understand the circuit operation. Okay. Next, so this is about the circuit operation. Now here, can we find the V0 average? What is the V0 average? Yes, can anyone? V0 average. No need to simplify even. By observing the waveform, we can tell the V0 average. Yes, V0 average. Yes, some are saying 0. Correct. V0 average is 0 only. Why? Because you can check here, it is a Vs V0 positive value. What this interval, this angle corresponding is pi minus alpha. And from pi till beta, what is this angle? This angle is also pi minus alpha. Na? So during pi to next 2 pi minus alpha. Okay. This angle is pi minus alpha, means this beta indicates your 2 pi minus alpha. Na? Same thing we have written here. Beta is equal to 2 pi minus alpha. Okay. So if this beta is 2 pi minus alpha, right? So this is your alpha to pi, and here it is pi to 2 pi minus alpha actually. Okay. So resultant average, if you check, that will be 0 only, right? Resultant average will be 0. Okay. Or we can simplify it with the expressions also. We'll be getting it as a 0 only. Okay. So how to write it as V0 average? Average output voltage. Average output voltage. Yes, V0 average is equal to 1 by 2 pi integration from alpha to beta. It is a Vm into sine of omega t na, d omega t. So which is equal to 1 by 2 pi integration from alpha to beta, means what? 2 pi minus alpha into Vm into sine of omega t. Right? So you can simplify it. Vm by 2 pi. What is the integration of sine? It is a minus cos of omega t, alpha to 2 pi minus alpha. So that this will be equal to V0 average. Therefore, V0 average is equal to Vm by 2 pi into, yes, minus cos of 2 pi minus alpha plus it is a cos alpha. Okay. cos of alpha. So this will be equal to Vm by 2 pi into, yes, this will be your minus cos of 2 pi minus alpha. It is a cos alpha only, right? Cos of 2 pi. Check the cosine waveform. You will understand. 0, pi by 2, pi, right? 3 pi by 2 and 2 pi, right? So waveform is like this. Okay. So this is your cos alpha, cos of alpha, na? So cos of omega t. Let me write cos of omega t. This is a cos of omega t. So what is the cos alpha and cos of 2 pi minus alpha? Cos alpha means, suppose this is alpha. So this indicates your cos alpha. Yes or no? And what is the cos of 2 pi minus alpha? If this is alpha, so can I say that this is like your 2 pi minus alpha? So what is cos of 2 pi minus alpha? Again, it is having the same value, na? So this will be your cos of 2 pi minus alpha, right? So cos of 2 pi minus alpha is again cos alpha only, and this is cos alpha plus. So minus plus 0, so that should be 0. Is this clear? V0 average is equal to 0, right? V0 average is a 0. Next, now can we find the I0 average? I0 average. We're having the expression for I0, na? Yes, we're having the expression for I0. Here it is. Vm by omega cos alpha minus cos of omega t. Okay. And I0 is non-zero from alpha till beta, na? Alpha till beta. So we can write I0 average is equal to, yes, 1 by 2 pi integration from alpha to beta. Yes. This expression. Vm by omega L into cos of alpha minus cos of omega t. Vm by omega L into cos of alpha minus cos of omega t into d omega t, right? So is equal to Vm upon 2 pi omega L, right? Into integration of cos alpha. So cos alpha is a constant term, na? Right? So it is like a cos alpha into omega t, right? Minus integration of cos of omega t. It is a sine of omega t. Limit alpha to beta. So this will be equal to Vm upon 2 pi omega L into, this can be written as a beta into cos of alpha, right? Minus alpha into cos of alpha minus sine of beta plus sine of alpha. Sine of alpha. Okay, this is the expression. Further, what we can do? We can put this beta is equal to 2 pi minus alpha. We can put beta is equal to 2 pi minus alpha, right? So this is the I0 average. It is clear. What is the conduction time of thyristor? Conduction time of thyristor. Yes, can anyone? Conduction time of thyristor. Thyristor T is in a on state from thyristor T is in a on state from omega T is equal to alpha till omega T is equal to beta, na? So conduction time is beta minus alpha by omega. Okay, beta minus alpha by omega. Further, we can replace that beta with 2 pi minus alpha. Okay, so beta minus alpha divided by omega, which is equal to, beta is equal to 2 pi minus alpha. So 2 pi minus alpha divided by omega, which is equal to 2 pi minus 2 alpha divided by omega, which can be written as 2 into pi minus alpha divided by omega, right? This is a conduction time of thyristor, right? Conduction time of thyristor. Okay. Next, what is the PIV rating of thyristor? PIV rating of thyristor. Yes, can you find the PIV rating? So for that, we need to draw the waveform of Vt. How will the waveform of Vt? This is omega t. Okay, 0 to alpha, alpha to pi, pi to beta, beta to 2 pi, right? And after 2 pi again, the same repeats. Okay, so how is the Vt waveform? 0 to alpha, thyristor is in a forward bias mode. Thyristor will be in a conduction mode state. It will be in a forward blocking mode. Na? So Vt will be same as that of the supply voltage. It is like this, right? Alpha to beta, thyristor is in a conduction mode. After beta, what will happen? It is like at beta, inductor energy becomes less than the supply energy. Thyristor will be in off state now. So what is the value? It is this type. Okay, reverse voltage. This type of waveform we getting, right? So either you can draw like this, or you can draw like this. Doesn't matter. This is supply voltage only, right? So and after 2 pi, the same again repeats. This is the waveform of Vt from alpha to beta. From alpha till beta, thyristor is in a on state. Okay, 0 to alpha, thyristor is in a forward blocking mode. Okay, and beta to 2 pi, thyristor will be in a, yes, beta to 2 pi, thyristor will be in a reverse blocking mode. Okay, so this is a reverse blocking. And this is a forward blocking, right? Next, so what is the PIV rating here? Come on, PIV rating of thyristor. Yes, PIV rating of thyristor. Vm sin beta, Vm sin alpha, Vm cos beta. Yes, the PIV rating will be V max only. Okay, I will let you know, is equal to V max, because you are thinking in a way like if alpha is less than 90 degree, in this way you are thinking, but we don't know na what will the how the consumer will use for what firing angle alpha, we don't know. So that's why we cannot specify that PIV rating in terms of Vm cos beta, Vm sin beta, Vm sin alpha. In that way we cannot specify. Please try to understand. Let us, yes, consider this circuit here. If you check here, if this alpha is less than 90 degree, if this alpha is less than 90 degree, definitely your beta will be greater than 270 degree. Na? Beta greater than 270 means you might be thinking that this is your Vmax. No problem. This is a Vmax only for alpha less than 90 degree. But suppose if your alpha is greater than 90 degree, then what will happen? Suppose if this alpha is greater than 90 degree, how is the waveform? From 0 till greater than 90 degree, we are having the wave shape like this, going to the peak value and again decreasing till this instant alpha. And we'll be having, yes, that alpha to pi, inductor stores the energy, na? And then pi to next beta, inductor releases the energy. Means in that case, your beta will be less than 270 degree. Are you getting the point? I am saying if alpha is less than 90 degree, your beta will be greater than 270 degree. If alpha is greater than 90 degree, the beta will be less than 270 degree. But while specifying the PIV rating, yes, we cannot specify that PIV rating depending on the alpha value, right? Because the user don't know, right? Or the manufacturer don't know this thyristor, whether the consumer or the user is going to use in which circuit for which load, we don't know. So generally, manufacturer need to specify the PIV rating in general way, right? So PIV rating is equal to Vmax. That is the maximum possible inverse voltage rating. And your maximum possible inverse voltage rating will be Vmax. And that is when alpha is greater than 90 degree. You can draw the V0 waveform for alpha greater than 90 degree. You can draw the VT waveform for alpha greater than 90 degree. You will realize what is the PIV here, why PIV is Vmax. Are you getting the point, right? So in general, we need to specify the PIV. We cannot specify the PIV just like a VM sin beta, VM sin alpha. No, we cannot specify the PIV in that way. Okay, we need to specify it in general way. Okay, next. Is this clear? Yes, VM is correct. Right? Yes. I will answer all your doubts at the end of the session. Okay. So next. So this is a PIV. Now, can we find the circuit turn-off time? Can we find the circuit turn-off time? Yes. Circuit turn-off time for thyristor. TC. For thyristor. TC means the circuit turn-off time. Yes. What is the TC for thyristor? Check the circuit operation. At omega t is equal to beta, current flowing through thyristor becomes 0. After that, the reverse voltage is maintained till 2 pi only, na? So it is a 2 pi minus beta divided by omega, right? 2 pi minus beta divided by omega. So it is a 2 pi minus beta divided by omega, which is equal to 2 pi minus in bracket 2 pi minus alpha divided by omega, na? So 2 pi will get cancelled. So it is like a alpha by omega. This is the circuit turn-off time for thyristor. Is this clear? TC for thyristor. Next, what about the output power? Output power or the load power. T0 average. It will be 0 watt only, na? Because you can check what is pure inductive load. Power, real power consumed by the inductor is always 0. Or you can check, you can take the product of these two, V0 and I0, and you can find the average value. You can find beta is equal to 2 pi minus alpha, means area under this is equal to area under this. One is a positive, second one is a negative. And if you take the product now, you will be getting the average will be 0 only, right? So P0 average will be 0 watt, right? So this is about the purely inductive load. Okay, purely inductive load. Next, let us discuss for RL load. Okay, RL load. Single phase half wave controlled rectifier with the RL load. With the RL load. Right? So circuit diagram same. The only thing is load element is changed. Vs this is the RL V0 I0 VT IT IS. Okay. So Vs, which is equal to Vm into sine of omega t. Ig get equals to thyristor alpha 2 pi plus alpha, right? Next. V0 the alpha pi 2 pi 2 pi plus alpha, and here it is a 3 pi, right? So let us discuss the circuit operation. Okay, VT waveform will draw at the end, right? So already in the yesterday's session we discussed the single phase half wave uncontrolled rectifier with RL load, right? And in that case we observed that I0 is slowly increasing, na, right? Till omega t is equal to alpha to theta. Till 0 to theta actually. From omega t is equal to 0 to theta, right? But here it will be like from alpha to theta. Okay, so let me draw the circuit. So yes, circuit operation, let us discuss. At omega t is equal to 0 to alpha, from omega t is equal to 0 to alpha, Vs is positive, so it is a plus here, minus here. So it is like thyristor is in a forward bias mode, but we have not applied the gate signal. So thyristor will be in a off state only. Okay, so from omega t is equal to 0 to alpha, for omega t is equal to 0 to alpha, right? If we, yes, draw the circuit, it will be like this. Vs plus minus, this is a Vt, this is a It, this is a Is, RL, V0 and I0, right? So thyristor is in which mode? Forward blocking mode. Okay, thyristor T will be in a forward blocking mode. Okay, so what is the current in the circuit? I0, It, Is, all will be 0, na? All will be 0 ampere. What about the V0? V0 is equal to 0 volt, right? Current is not flowing, na? Right? So that's why your V0 is equal to 0. What about the Vt? You can apply KVL to loop. So Vt will be equal to like a plus Vs minus Vt minus V0 is equal to 0. In that V0 is 0, na? So therefore Vt is equal to Vs. That is thyristor voltage is same as that of the supply voltage, na? So you can check during this interval V0 0 volt. Okay, I0 is 0 ampere. So here V0 should be equal to 0 volt. I0 also equal to 0 ampere. Okay, this is from 0 to alpha. At alpha, we are going to apply the gate pulse to the thyristor, na? At alpha, we are applying the gate pulse to thyristor. So when the gate pulse is applied to thyristor, thyristor will immediately turn on. Thyristor turns on, so current starts flowing in the circuit. Yes or no? Right? Inductor go on storing the energy. Inductor go on storing the energy. This will continue till theta only. This will continue till theta only. Okay. Some of the local books they have given from alpha to pi, inductor is storing the energy, like this statement they have given. No. Inductor will store the energy only till alpha, from alpha till theta only. From alpha till theta. So what is the theta? We need to discuss what is the theta. Okay. So theta means actually the instant. Theta means the instant till which your VL is a non-zero and positive. VL is a non-zero and a positive. In the yesterday session we discussed at theta, at omega t is equal to theta, what was happening? Yes, it is like a Vs from 0. In the yesterday session we discussed from omega t is equal to 0 till theta. It was like a Vs was greater than that of your VR, na? So Vs is greater than that of the VR. So VL is equal to Vs minus VR. We discussed. So that's why your VL was positive, right? And as theta reaches, as the omega t reaches the theta, okay, our VR go on increasing because VR will be like in phase with your I0, like this case. Okay, so let me draw. For omega t is equal to alpha till theta. For omega t is equal to alpha to theta. Yes, thyristor is in a conduction mode. supply voltage here it is R L. This is a Vs plus minus. This is a Vt. This is a It. Here it is Is R L. This is V0. Here it is a I0. This is a VR, and here it is a VL. Na? So during this interval, what is Vt? Vt is equal to 0 volt. Okay. Next, what is the V0? V0 is equal to Vs, same as of the supply voltage. V0 is equal to Vs. We can apply KVL to this loop. We can apply KVL to this loop. Yes or no? Right? So KVL to this loop will be like a V0 minus VR minus VL is equal to 0. So therefore, VL is equal to V0 minus VR. Na? But what is V0? V0 is equal to Vs only, right? So I can write it as a Vs minus VR. This is your VL. So during this interval, if you check here, wherein the waveform will be like this, because inductor go on storing the energy. Inductor go on storing the energy. So it will be like this. Till theta. Theta is a near to pi. Theta is a near to pi. Till theta, inductor stores the energy. Till theta, inductor stores the energy. Okay. So corresponding to this instant, V0 is equal to Vs. Na? So corresponding to this instant, let me write here theta. This is a theta. Inductor stores the energy. And V0 will be same as that of the supply voltage. This is your theta. Right? Same as that of supply voltage. Till theta. If we want to draw the waveform of VR also, okay, we can draw the waveform of VR also. This is till theta. From alpha, VR starts, okay, and till theta, it will be like this. It will be in phase with the V0, na? Because according to Ohm's law, what is the voltage across resistor? Current flowing through the resistor into resistance value. Current flowing through the resistor is I0 only. So I0 is having this type of nature. So definitely your VR will be like this only. Okay. So VR, this is nothing but your VR. This is a VR. And the difference between supply voltage and VR, difference between supply voltage and VR is nothing but your VL. Okay. So if you check at omega t is equal to alpha, your VL will be like this. This much value VL will be having. As theta increases, as omega t increases, your VR also increases, na? Because I0 also increasing. At theta, at omega t is equal to theta, VR and Vs both are same. This is Vs, na? Right? This is a Vs. At omega t is equal to theta, VR and Vs both are same. So your VL will become 0. This indicates VL will be 0. Before omega t is equal to alpha, yes, what will be the value of VL? My question is, before omega t is equal to alpha, what will be the value of VL? Yes, can anyone? Before omega t is equal to alpha, what will be the value of VL? Come on, speak out. Yes. Zero only, right? Zero only, because whatever the source voltage is there, the full source voltage, yes, was appearing across the thyristor. Now we discussed from 0 to alpha. From 0 to alpha, we discussed this case. Yes, Vt is equal to Vs. So if Vt is equal to Vs, okay, means whatever the source voltage is there, this full will appear across the thyristor. Voltage across load will be 0. And V0 is equal to VR plus VL. Na? V0 is 0. VR will be 0 only because I0 is 0. Na? From 0 to alpha, I0 is 0. So VR is also 0. V0 is also 0. Your VL will be also equal to 0. Okay. So please keep it in mind. From omega t is equal to 0 to alpha, VL will be 0 only. Right? VL will be 0. Okay. VR also equal to 0. Okay. So after alpha, what will happen? Your VR starts increasing. This below, yes, this blue line is nothing but your VR. Huh? This blue line is nothing but VR. Let me indicate here. Yes. This blue line is a VR. This blue line is a VR. Okay. And this shaded indicates your VL. This shaded indicates your VL. voltage across inductor, because it is the difference between supply voltage and a VR. So this voltage at this instant, it is a Vs is this value, na, and VR is 0. So that's why this difference is nothing but your VL. So you can check whether it is a positive high value. This is a non-zero value. This is a 0 value. So this is a positive. From this instant till this instant, you can check from alpha till theta. You can check Vs is greater than VR. So your VL is a positive only. VL positive means L di 0 by dt will be positive. L di by 0 dt is positive means your di 0 by dt is positive. Di 0 by dt is positive means inductor is storing the energy, right? Same thing we discussed. Next, this will continue till theta. After theta till pi, what will happen? From theta till pi, because after theta, what is happening? Your Vs is less than VR, no? Right? So from theta till pi, for omega t is equal to theta to pi. Omega t is equal to theta to pi. Yes, what is happening? Now Vs is less than VR. Vs is less than VR. So as Vs is less than VR, so it is like your VL will be negative. Yes or no? VL will be negative. So now inductor will go on releasing the energy. So equivalent circuit will be like this. Vs is positive only, but Vs value is less than VR. This is the V0, I0. This is a VT. This is a IT, and here it is a IS. So what is happening in the circuit? Now in this circuit, Vs is a less than VR. Vs is a less than VR. Okay. So therefore you can check. Actually, thyristor will be in off state on state only, because inductor is releasing the energy. Okay. So V0 will be equal to Vs only. Vt is 0. V0 is equal to Vs. V0 is equal to Vs, and here we are having the V0 is equal to VR plus VL, na? Next, so therefore VL is equal to V0 minus VR. But we know V0 is a Vs, na? V0 is equal to Vs. So this is a Vs minus VR. So what is this Vs minus VR? It will be positive or negative? It will be negative, because Vs is less than VR. Okay. So therefore VL is a negative. VL negative means what? What this indicates? VL is negative. It indicates that inductor is releasing the energy, right? Inductor is releasing the energy. So here inductor releases the energy. Okay. But inductor energy and supply energy, both will be assisting, both will be adding. Okay. So let me write inductor L releases energy, releases energy. So during theta to pi, what is happening? V0 is Vs. I0 will be decreasing and VL is negative. Okay. So let me draw this waveform. Yes. Theta to pi, V0 will be same as that of the Vs. So it is like this. This type of waveform, same as that of the supply voltage will be getting, right? Same as that of the supply voltage. I0 will be decreasing because VL is a negative. I0 is a decreasing because VL is negative. And next, what about the VR? VR is, yes, like this. I0 decreasing means definitely VR also decreasing, na? So VR wave shape will be like this. So this is a VR. This type of waveform will be getting for VR. And what is the difference between VR and Vs? That will be your VL now. That will be the VL. So VL will be like this. This type of VL will be getting. Okay. From theta till pi, I'm saying. From theta till pi. After pi, what will happen? Supply voltage is reversed, na? After pi, supply voltage is reversed. Okay. So from or for omega t is equal to pi till beta, supply voltage is negative now. So minus here plus here, this is Vs. But whether the inductor will allow the sudden reversal of the current through it? No. So inductor will continue go on releasing the energy. RL, this is a V0, this is a I0, this is a VT, it is IT, it is IS, right? So inductor will release energy in opposition to that of the supply voltage, right? Are you getting the point? Okay. Now here you can check. Yes. Inductor releases the energy. or let me show here. This is a VR na, and this is a VL we are having. In this case also VT is 0. Next VT 0. What about V0? V0 is equal to Vs, right? Now what about the further we can write V0 is equal to VR plus VL na, VR plus VL. Okay, therefore VL is equal to what? It is a V0 minus VR, but V0 is same as that of the supply voltage, Vm into sine of omega t. Definitely it will be negative, minus VR. This is your VL. Okay, so you can check here. Actually the supply voltage is negative, and this minus VR will be getting there. Okay, added. So it is like a reverse negative voltage will be getting across VL, and it will be addition of the two voltages, VR and VL. So you can check the waveform. It will be like this. Yes, from theta till pi, it is like inductor releases the energy. So from pi till beta, because we are discussing from pi till beta. It is like this. This will be till beta only. Okay, till beta, your V0 will be same as that of the supply voltage, right? Next, but it is negative, so that's why this is also negative. And here I0 is decreasing, so your VR also decreasing. So VR will be like this, and yes, this will be your VL. Shaded will be your VL, right? So this will continue till beta. After beta till 2 pi, what will happen? Yes, so this V0 should be minus Vs. If we take it as a minus plus, so this should be minus Vs. Okay. Next, this will continue till beta. After beta till 2 pi, what will happen? From beta till 2 pi, it is like a inductor is not having energy to release now. Okay, so that's why circuit will be at the rest position. Thyristor off state, R L Vs minus plus, this is Vt, this is It, Is, RL and V0. Okay, so here circuit will be at the rest position, so that's why your currents will be 0. It, I0, Is all will be 0. Okay, V0 is equal to 0 volt. Vt, right, you can apply KVL, you will be getting Vt is equal to minus Vs. Vt is equal to minus Vs. Okay, so we'll be getting the waveform like this. Yes, this is a 0, this is a 0. Okay, and after 2 pi the same cycle repeats now. So again this will be like this, theta in this instant, like this waveform, right? So this type of waveform we are getting. So circuit operation is same as that of the last case, whatever discussed in the yesterday session. The thing is, in the yesterday session, it was like starting from 0. Means it is like alpha equal to 0 means for the thyristor if alpha equal to 0 means you will be getting the waveform of a diode rectifier like this. Are you getting the point? Okay, so same, right? So we'll take a break here. After the break, we'll derive the expressions, right? And after that, we'll be discussing about the RL load with freewheeling diode.
Yeah, hello. Sir.
Yes. Within 2 minutes, please complete it. Within
Yes, sir. 29 slides, sir.
29
slide. Yes, sir.
Huh.
That's V not equal to minus V. That's it, sir. No.
Okay, na?
You have changed it, sir. You have changed it. No.
Yes. Actually, yeah, because this polarity I reversed, so I need to write that minus V. Right.
That's it, sir.
Okay.
Sir.
Yes, please.
From theta to pi, why are we not reversing the polarity of VL? We are not representing now.
From theta to pi,
we are not representing the polarity of VL is reversing.
Yesterday also I told you the same thing. Here, throughout the power electronics, we are not going to reverse the polarity of the VL. Is this clear?
Okay, sir.
We are going to keep the same polarity, but for this polarity, if VL is positive, the meaning is inductor is storing the energy. For this
Okay.
polarity, if VL is negative, the meaning is inductor is releasing the energy. Is this okay?
Okay, sir.
So please don't ask me again that, sir, why you are not reversing the polarity and those things. Okay?
Sir. थोड़ा confusing है. That's why.
Yes, yes,
That's why I
yes.
asked.
Okay, okay.
Hello, sir.
Yes.
Pure inductor circuit.
Pure inductive circuit.
In the circuit, exactly inductor stored time is equal to releasing time, sir. Even though alpha we should vary.
Yes, yes, you can increase the value of alpha. Because
sir,
the thing,
after
what is
90
happening here, if you increase the value of alpha, then inductor is getting a less time to store the energy.
Sir.
You can check now, if alpha is 120 degree, then inductor will be getting hardly 60 degree to store the energy, right?
Yes, sir.
So therefore, if inductor is getting 60 degree to store the energy, means inductor will store the less energy.
Okay, sir.
So after pi, what will happen? Inductor will take a less time to store, release the energy. That is only 60 degree,
Okay.
right?
Okay.
Okay. Or you can check with this expression of I0, na, whatever the expression we have written. This expression of I0 is valid for this interval also. Let me tell you, for this interval also, this expression, right? Pi to beta also, this expression is valid. Because the thing is, from, yes, alpha to pi and pi to beta, we are getting this circuit only, na?
Yes, sir.
You can check alpha to pi also thyristor is in on state.
Yes, sir.
Pi to beta also thyristor is in on state, na?
Okay, sir.
Here we are having the supply voltage Vs, and if from alpha to pi also we had a supply voltage Vs only.
Okay.
So you can check or you can derive the expression for I0 for this circuit. You'll be getting the same expression, right? You'll be getting this expression only,
Okay.
right? So,
Yes, sir.
okay, we'll take a break here. Other questions we'll discuss at the end. Okay, it's a 7. We'll start at 7:20, right? Okay. So now we are going to derive the expressions, okay, for RL load, single phase half wave control rectifier with the RL load, right? So one by one, let us derive the expressions. V0 average is equal to, if you check the V0 waveform, whatever the waveform we are running from 0 to 2 pi, right? The same is repeating from 2 pi to 4 pi. So periodic angle is 2 pi. And in that also the effective interval is from alpha till beta. Okay, alpha till beta. So let me write it as V0 average is equal to 1 by 2 pi integration from alpha to beta, right? It is a Vm into sine of omega t into d omega t. Okay, so we can write it as, which is equal to Vm by 2 pi into integration of sine is minus cos of omega t alpha to beta. So this will be Vm by 2 pi into cos alpha minus cos beta, cos of alpha minus cos of beta, right? This is the V0 average, correct? V0 average. Next, what about the I0 average? Yesterday we discussed the average voltage across inductor is 0. Okay, so I0 average will be equal to your V0 average divided by R. V0 average is, V0 is equal to VR plus VL, na? And in that also VL is also VL is having a average voltage is 0. So that's why your I0 average is V0 average by R. Next, V0 RMS. V0 RMS is equal to 1 by 2 pi integration from alpha to beta Vm square into sine square of omega t into d omega t to the power 1 by 2, right? Same, it is a Vm upon root 2 pi into, we can write it as a integration from alpha to beta 1 minus cos of 2 omega t divided by 2 into d omega t. Same steps we are following, alpha to beta to the power 1 by 2, right? So is equal to Vm upon 2 root pi into, this can be written as a omega t minus sine of 2 omega t by 2 limit alpha to beta to the power 1 by 2, which is equal to Vm upon 2 root pi into, we can write it as beta minus alpha minus sine of 2 beta divided by 2 plus sine of 2 alpha by 2 to the power 1 by 2, right? This is a V0 RMS. Next, conduction time of thyristor. Conduction time of thyristor. Yes, conduction time of thyristor is equal to, thyristor is in on state from alpha till beta. Okay, so conduction time is beta minus alpha divided by omega. Okay, beta minus alpha by omega. Next, PIV rating of thyristor. PIV rating of thyristor. So for that we need to draw the waveform of VT, right? Waveform of VT. Yes. So PIV rating of thyristor. So VT waveform we can draw VT. Zero to alpha, alpha to pi, pi to beta, and beta to 2 pi, right? So VT will be like this: 0 to alpha, thyristor forward blocking mode, na? Alpha to beta, thyristor is in a conduction mode. and beta to 2 pi, thyristor is in off state, right? So we'll be having this type of waveform. Correct? So what is the PIV rating? It is a Vmax. Okay, Vmax. So let me write PIV of thyristor T is equal to Vmax. Is equal to Vmax, right? Next, what is the circuit turn-off time? TC for thyristor. TC for thyristor. Yes. Circuit turn-off time for thyristor. Yes, can anyone? At which instant the current flowing through thyristor becomes 0? Yes, circuit turn-off time for thyristor 2 pi minus beta, right, divided by omega. Correct. So 2 pi minus beta divided by omega. 2 pi minus beta divided by omega, right? This is the circuit turn-off time for thyristor, right? Next, I0 expression. Here, yesterday also I told you I0 RMS we are not going to find for REL load, okay? Because the expression for the I0, right? We are having a very big expression and we cannot directly find here I0 RMS, okay? And input power factor also. For input power factor with REL load and RELE load, okay? We are going to discuss at the end of the rectifiers actually, okay? At the end of the single phase rectifier specifically, right? So let us find the I0 expression, okay? So for omega t is equal to alpha to beta. If you check for omega t is equal to alpha to beta, we're having the circuit like this. Thyristor is in a conduction mode. Only during this interval, the I0 is non-zero, na? Right? So R and L. This is like a Vs, okay? Vt, R, L. This is a V0 and here it is a I0, right? So if we apply KVL to this loop, yes, KVL to loop. It is like a plus Vs minus R into I0 minus L into di0 by dt is equal to 0, right? So this can be written as di0 by dt, okay, plus R by L into I0, okay, which is equal to Vs means Vm into sine of omega t divided by L, right? So this is the differential equation in standard form, okay? So if you want to simplify it, yesterday I told you how to simplify by finding the integrating factor, and solution is like y into integrating factor is equal to integration of q into integrating factor into dx plus c, in that way, okay? So if we simplify it, we'll be getting I0. It is similar to that of the yesterday's case. The only thing is here alpha will be getting added, okay? Alpha will be getting added. So it is a Vm upon mod z, okay, into sine of omega t minus theta. Now actually the thing is yesterday, yes, also we consider theta is this angle, huh? But there is a little bit confusion, so that's why we're going to change the angle, right? This is here we consider the theta, na? So instead of that theta here, now in this expression, let me indicate it as a phi. I will tell you what is the phi actually, okay? Minus Vm upon mod z, okay, into sine of alpha minus theta. In the yesterday's expression, it was like a sine of 0 minus theta. So sine of minus theta will be like your minus sine theta, okay? So that's why this minus and this minus, it was a plus here, okay? So this is sine of alpha minus theta into e to the power minus r by omega L into omega t minus alpha. This is the expression. No need to memorize the expression, right? Till time they haven't asked any question based on this expression, okay? Right? So this is only for information, okay? So yes, this is the I0. This is the I0, and with by using this I0, can we find the I0 RMS? No, it is very difficult to find the I0 RMS, right? So this is only for the information, okay? Only for the information. Where? Yes, this is phi. Let me write it as a phi. Yes, where mod z is equal to under root r square plus omega L bracket square, and phi is equal to impedance angle tan inverse of omega L by r. In the yesterday session also, please correct in the notes. Actually, I couldn't correct it. Okay, but please correct in the yesterday session whatever the I0 expression I gave na. In that case, I wrote here theta, but this theta, okay, whatever I wrote in the yesterday session, that theta, and in the waveform we are having one theta. Okay, so it is getting confused. So please correct that theta, replace the theta with a phi. In the I am repeating, in the yesterday session, for single phase half wave uncontrolled rectifier, okay, we are having one I0 expression. For RL load, we are having one I0 expression. In that I0 expression, we wrote Vm by mod z into sine of omega t minus theta. Please correct, replace that theta with a phi. Replace that theta with a phi. Don't use the theta there, okay, because it will create a confusion. We are having a theta in a waveform also, but that theta and if whatever we wrote in the yesterday's I0 expression, that theta both are not the same. Please correct that theta with a phi. Okay, please put here phi, right? So phi is a different, theta is a different, right? So here also it is a sine of alpha minus phi. In the yesterday session, it was like a sine of theta. Replace that theta also with a phi. Please replace that theta with a phi. Correct it. Okay. So next. So this is only for over and above case we can say. Okay. So it is they haven't asked any question related to this expression till now. Okay. So in any of the examination, right? So yes. So this is for RL load. Okay. For RL load. Now if you check the waveform for RL load, and if you compare this waveform of V0 with the R load, okay, V0 waveform in this case, and if we compare the V0 waveform in case of purely resistive load, in which case the V0 average will be more? In which case the V0 average will be more? Whether the V0 average will be more in RL load or whether it will be more in purely resistive load? Yes. You can recall the V0 waveform in a purely resistive load. We are having a V0 in purely resistive load. It is like from alpha to pi. It is same as that of the supply voltage. But from pi till 2 pi in purely resistive load, from pi to 2 pi, we are having V0 is a 0 na. Here we are having a negative value na from pi to beta. So if we compare this V0 and purely resistive load V0, in which case the average value will be more? Come on. Purely resistive, some are saying RL load, R load. Okay. Please listen. In case of purely resistive load, the average value will be more. Why? Because you can check here for RL load, we are having this negative pulse na? From pi to beta, V0 is negative. And while finding the average value, what we are doing? We are adding this plus adding this na. So what about the, yes, area under this pulse? Area under this pulse will be negative only. Area under this pulse is positive. So if I add the entire area, so it will be like a resultant average will be decreasing only in this case. Okay, so this is the drawback of this circuitry. If the load is RL load, okay, and we are having only thyristor connected in the circuit, okay, here compared to that of the purely resistive load, we are getting the V0 average is a somewhat lesser. We are getting the V0 average is a lesser. Why it is a lesser? Because of this negative V0. Because of this negative V0. Okay. So in order to avoid this, generally a freewheeling diode is connected. Freewheeling diode is connected across the load. Freewheeling diode is connected across the load. Okay. So now we are going to discuss that single phase half wave control rectifier, RL load and with the freewheeling diode. RL load and with the freewheeling diode. Let us discuss the circuit operation. Yes. Let me write here. In this circuit, V0 is a negative. V0 is a negative from omega t is equal to pi to beta. Okay, from pi to beta, V0 is negative. Okay, it will cause. So therefore, V0 average, right, will be lesser than that of purely resistive load. Purely resistive load. Okay, purely resistive load, right? So in order to avoid this, generally a freewheeling diode, a freewheeling diode is connected across load. Okay, so now you can check in this circuit from pi to beta. What is happening in the circuit from pi to beta? Why the V0 is negative from pi to beta here? Because from pi to beta it is like a supply voltage is negative and inductor was releasing the energy in opposition to that of the supply voltage, and our thyristor was in a conduction mode. So due to that, our V0 was same as that of the supply voltage. So supply voltage is negative, so V0 is also negative. So now in next configuration, what we are going to do? We are going to provide, yes, the alternate path for the inductor to release the energy during this interval, that is during pi to beta only. Okay, so the circuit diagram, yes, let us discuss the next configuration. Single phase half wave, single phase half wave controlled rectifier, RL load, and with a freewheeling diode, So we are having now RL load and a freewheeling diode also in the circuit. So circuit diagram. So here we are having a diode connected. This is a VS, thyristor T, yes, IS, IT, VT, diode D, right? But let me write it as a DF. DF means a freewheeling diode. This current is, let us write it as a IFD, freewheeling diode current, RL, V0, and here it is a I0, right? So yes, the waveforms. Supply voltage, pi, 2 pi, 3 pi, right? Gate pulse to thyristor. Alpha, here it is 2 pi plus alpha. Let me draw the V0 and I0 waveforms on the same plot. This is the V0, I0, till theta it will increase. Okay, After that, it will decrease until beta. This type of waveform. Is alpha, pi, beta, 2 pi, 2 pi plus alpha, 3 pi, right? Conducting devices are alpha to pi, thyristor T1, sorry, thyristor T conducts, pi to beta, freewheeling diode conducts. Okay, DF. Same is happening here. Okay, so VT waveform we will draw at the end, right? So single phase half wave control rectifier with RL load and with freewheeling diode. The circuit operation during omega t is equal to alpha till omega t is equal to pi is same as that of the previous case. That is for whatever we discussed for RL load now. The same circuit operation will be will hold here for omega t is equal to alpha to pi. But after pi it will different. After pi it will different. Okay, so let us discuss in short. I am explaining because the same circuit operation we discussed for RL load also. Okay, so for alpha to pi, what is happening in the circuit? Let us discuss. Okay, so for alpha to pi, yes, in that we are having alpha to theta and theta to pi actually. Okay, so alpha to theta it is like a supply voltage is positive. Yes, thyristor T will be in a forward bias mode, conduction mode. Current will be flowing from Vs, thyristor, load, and again back to the Vs. In this loop, the current will be flowing. V0 will be same as that of the supply voltage. Okay, I0 will be increasing slowly. Okay, so you can check from alpha to theta. If you check, theta means somewhat here. Okay, this is like your theta. So alpha to theta, yes, it is like a V0 is same as that of the supply voltage. Thyristor T will be in a conduction mode. So thyristor T is in a conduction mode. V0 will be same as that of the supply voltage. Okay, I0 is increasing slowly. This will continue till theta as that of the previous case. Okay, after theta what will happen? After theta what will happen? Yes, this inductor will release the energy, okay, through the thyristor T till pi. From theta till pi, inductor will release the energy through this thyristor. You can check the circuit. From theta to pi, your freewheeling diode will be in a reverse bias mode only. You can check here from theta to pi. If you check what is the voltage across freewheeling diode, let me write it as a VDF. Can I say this VDF is equal to minus V0? Is this clear? Can I say this VDF is equal to minus V0? Yes or no? Because these two are connected in anti-parallel just like na. Because for V0 it is a higher potential, here it is a lower potential. And similarly for VDF, this is a higher potential, here it is a lower potential we have considered. Okay, so you can apply KVL to this loop also. Minus VDF minus V0 is equal to 0. So your VDF is equal to minus V0. VDF is equal to minus V0. Is this clear? Right? Now here VDF. So diode will be if we, as VDF is equal to minus V0, VDF is equal to minus V0 here, right? So if V0 is a positive, if V0 is positive, then it is like a VDF is negative na. If V0 is positive means this is minus of this positive value, so it is like a negative VDF. So diode DF will be in which mode? Reverse bias. Okay, reverse bias. Next, if V0 is negative, then VDF will be positive na. VDF will be positive. Okay, because if V0 is negative, negative of negative, so it is a positive. Then DF will be your forward bias. DF will be in a forward bias. So now you can check here during alpha till theta. Yes, it is like during alpha till theta, V0 is positive only. Your freewheeling diode will be in a reverse bias mode. Okay. Next, after theta, inductor will be, yes, releasing the energy through the thyristor T. Okay. So when inductor releases the energy through the thyristor T, again V0 is equal to Vs. V0 is equal to Vs. I0 will be decreasing slowly because inductor is releasing the energy, same as that of the previous case. This will continue till pi only. After pi, what will happen? That is important in this case. Okay, after pi, supply voltage is reversed. After pi, supply voltage is reversed. So you can check if supply voltage is reversed, it is like lowest potential. Yes, this is like a highest potential is appearing here. Okay, and now you can check here with this supply voltage will try to circulate current in this direction. Okay, supply voltage will try to circulate current in this direction. And near to the pi, if you check, the load current is a non-zero now. Near to the pi, load current is a positive, and non-zero means what? Current flowing through the inductor is in a downward direction. So after that, whether our inductor will allow the sudden reversal of the current through it? No. So what will happen? Now inductor is having the two paths available to release the energy. One is inductor can either release the energy through the freewheeling diode, or inductor can release the energy in opposition to that of the supply voltage. Please listen it carefully. From pi to beta, what is happening in the circuit? After pi, supply voltage is reversed. So inductor is now having the two paths available. One is inductor can release the energy through the freewheeling diode. Inductor can release the energy in opposition to that of the supply voltage. But we know the tendency of the current. Current always follows the path with lesser opposition. You can check if inductor releases the energy in this loop, that is same as that of the previous case, then to the inductor energy or to the inductor current, whether there will be the opposition of the supply current. Yes. Are you getting the point? Okay. Inductor energy will be having the opposition of the supply energy. But whereas if the inductor releases the energy in this loop, okay, so whether it will be having any opposition in this loop? No. So that's why inductor current or the inductor will release the energy through the lesser opposition path, that is nothing but through the freewheeling diode. So from pi to beta only this is happening. Before pi, you can check your freewheeling diode will be in a reverse bias mode only. Before pi, your freewheeling diode will be in a reverse bias mode. So you might be thinking, sir, from pi to beta only, why inductor is releasing the energy through the freewheeling diode? Why not from theta to pi? From theta to pi, you can check the freewheeling diode voltage. Freewheeling diode voltage is equal to your minus V0. Or in other way, in other words, how we can represent this? Yes, this can be written as, this is a VR na, and this is VL. So VDF is equal to what? We can apply the KVL to this loop. It is a minus VR, minus VL, minus VDF is equal to 0. No? Minus VR, minus VL, minus VDF is equal to 0. So let me write here also. Yes, this also minus VR minus VL minus VDF is equal to 0. So therefore, what is VDF? VDF is equal to minus VR minus VL. Na? VDF is equal to minus VR minus VL. Now you can check. Okay, now you can check from omega t. From omega t is equal to theta to pi. From omega t is equal to theta to pi, what is this value? From omega t is equal to theta to pi, definitely from theta to pi VL is negative na, because inductor is releasing the energy. But whether the inductor value, inductor voltage is greater than the VR voltage or less than the VR voltage, that we need to understand. From theta to pi, yes, VL is from theta to pi, VL is a negative. Okay, from theta to pi, let me write from omega t is equal to theta to pi. Yes, VL is a negative. VL is a negative. Okay, VL is negative, it is okay. But as if VL is negative, so minus of that negative means definitely this will be plus. But we need to check whether the magnitude of the VL is less than VR or greater than VR. You can check a circuit diagram or you can check the waveform. Okay, how is the waveform we are having? If I want to draw the waveform of VR, it will be like this. Now VR we discussed. It will be like this, increasing, and after that it is a decreasing. This is VR we are having. And we know how is the VL. VL is like this. Na? Sorry, from alpha only it will start. I'm sorry. This is a controlled. Na? So that's why from alpha it will start. So it will be like this. From here it will start. This is alpha. This is alpha. So from alpha till this theta, na? This is like your theta. Okay. So from alpha till theta, yes, what is your VL? We discussed the VL is this difference, na? VS minus VR. This is your VL. So VL is this one. At theta, VL is 0. At theta, VL is 0. So alpha to theta, VL is positive. After theta, VL is negative. Now you can check from theta to pi. From theta to pi, VL is negative, it is okay. But from theta to pi, theta here and here it is a pi. What is VL? VL is a VS minus VR. Na? So you can check VL is from theta to pi, VL is only this value. VL is like Yes, this shaded region after theta. So you can check from theta to pi. From theta to pi, you can check what is VR value from theta to pi. VR means this red curve, that is a VR. And VL means that vertical line I have drawn, na, vertical blue line, that is nothing but your VL. At omega t is equal to theta, VL is 0. After theta, as we move towards the pi, after theta, as we move towards the pi, your VL is increasing. VL is increasing. But between theta to pi, between omega t is equal to theta to pi, VL is less than VR only. Are you getting the point? Why VL is less than VR? I am saying because VL means it is a difference between VR and VS, na? Right? So after theta, as we move towards the pi, your VL is increasing. At omega t is equal to pi, your VR and VL both are same. You can check the circuit waveform. Okay. At omega t is equal to pi, you can check at omega t is equal to pi, VR is here and VS is 0, na? So what is the VR and VL? VR and VL both are same. So between theta to pi, magnitude of VL is less than VR. So as the magnitude of VL is less than VR, as this magnitude of VL is less than VR, so I am saying magnitude because we know from theta to pi, VL is negative. I am using the word magnitude here. Okay. So you can check if VL is VL magnitude is less than VR. So this difference or this, okay, this value will be negative only. So your freewheeling diode will be in the off state. That is a reverse bias mode. But after theta, after pi, what will happen? After pi, you can check we are having VL like this now. After pi, this is VL we are having. So now you can check from pi till beta. From pi till beta, what is VL? VR is this red one indicates that VR, and VL means that vertical line, blue, that indicates your VL. So you can check here. After pi, you can check VL is from this point to this point. This is the VL's magnitude. This full. Let me use the different color. Yes. From this point to this point, we are having a VL. But what is the VR? VR is only from this point to this 0. This is a VR. So you can check VL is greater than VR. If VL is greater than VR, magnitude of VL is greater than VR, your freewheeling diode will be in a forward bias mode. So please keep it in mind. Okay. From omega t is equal to pi till beta only, your freewheeling diode will be in a forward bias mode. Right? Before pi, freewheeling diode will be in a reverse bias mode only. That's why, yes, before pi, inductor cannot release the energy through the freewheeling diode. Right? Please try to understand this shaded region, what it indicates. It is the values of VL. At alpha, VL is maximum. Because you can check na, in transient response network theory, what we do before switching, if inductor current is 0, then at the instant of switching, inductor will act as an open circuit. So inductor is acting as an open circuit means voltage across inductor will be high. So highest voltage will be at omega t is equal to alpha. After that, as we move from that switching instant to the steady state, at steady state, what is happening? Your inductor is acting as a short circuit, na? Yes or no? Right? Inductor acts as a short circuit at steady state. So at steady state means in our circuit, it is like a theta. So here voltage is maximum from alpha till theta. As we move as we increase omega t from alpha till theta, your VL go on decreasing. At theta, VL becomes equal to 0. After theta, VL increases, but it is a negative. Is this clear? Right? So your freewheeling diode will be in a forward bias mode only from pi to beta. Okay, pi to beta. Okay, so let me write DF will be in forward bias mode. In forward bias mode only from omega t is equal to pi to beta. So during pi to beta, what will happen? During pi to beta, yes, we can draw the equivalent circuit. It is like freewheeling diode will release the energy. Yeah, sorry, inductor will release the energy through the freewheeling diode. Okay. So from pi to beta. So for omega t is equal to pi to beta, circuit will be like this. Supply voltage, thyristor, freewheeling diode conduction mode, and here it is a R, here it is a L, right? This is a VS, minus plus pi to beta means Vs negative, right? This is a Vt, this is a It, this is a Is. Okay, this is a freewheeling diode df, voltage across freewheeling diode Vdf, current flowing through freewheeling diode, right? IFD were written. So this is RL, this is a V0 and the I0. Now you can check in this circuit, when inductor releases the energy through the freewheeling diode, means in this loop the current is flowing. Okay, so what will happen means freewheeling diode is in a conduction mode. So as freewheeling diode is in a conduction mode, what will happen to the thyristor? Thyristor will be in a off state now, because due to the reverse voltage, thyristor will be in a off state only. Okay, so thyristor T is in a off state. Freewheeling diode will be in a conduction mode. Okay, will be in a conduction mode. So now when inductor releases the energy through the freewheeling diode, what is the V0? V0 is equal to 0 volt, because voltage across the conducting diode. Okay, so means potential difference between these 2 points is equal to potential difference between these 2 points. Now this potential difference is equal to this potential difference, right? So therefore V0 is equal to 0 volt, right? What about the Vt? Vt you can apply KVL here, right? You will be getting plus Vs plus Vt is equal to 0. So Vt is equal to minus Vs. Vt is equal to minus Vs. Is this clear? Why the output voltage is 0 here? Because inductor is releasing the energy through the freewheeling diode. But whereas in the previous case, if you check, freewheeling diode was not there, right? So that's why inductor had only one path available to release the energy, and that path was through in opposition to that of the supply voltage. Here inductor is having the alternate path available, and as we know the tendency of the current is it follows the path with lesser opposition, right? So that's why inductor will release the energy through the freewheeling diode, right? So Vt is equal to minus Vs. This is from pi to beta. Omega t is equal to pi to beta. After beta, what will happen? After beta, it is like a circuit will be at the rest position. So we can write same circuit as that of the previous case. From omega t is equal to beta to 2 pi. Omega t is equal to beta to 2 pi. Yes, it is like a circuit will be at the rest position, means now at beta inductor has released the energy fully. Inductor is not having any energy now to release it. Okay, so that's why circuit will be at the rest position. Both the diodes will be in an off state. Vs, Vt, It, Is, freewheeling diode. This is your VDF, RL, V0 and I0. Now you can check if this is the circuit, whether the current will flow from source towards the load. No, right? So therefore I0 is equal to 0. V0 also equal to 0. What about the Vt? You can apply KVL to the outer loop. You will understand. KVL to the outer loop. So KVL to outer loop. So it is like a minus Vs, sorry, beta to 2 pi. It should be opposite, minus plus. Okay, so it is like a plus Vs plus V0 plus Vt is equal to 0 now. So here V0 is 0 we are having. So therefore Vt is equal to minus Vs, right? Vt is equal to minus Vs. Is this clear? So this is about the circuit operation. Now we can draw the waveform of Vt also, and if required we can draw the waveform for VDF also. So Vt 0, pi, beta, 2 pi, right? And again 2 pi plus alpha. Yes, from 0 to alpha, what is Vt? From 0 to alpha, what is Vt? Come on. Thyristor will be in a on state, off state, forward blocking, forward conduction. 0 to alpha, thyristor will be in a which mode? Yes, forward blocking, right? Thyristor will be in a forward blocking mode. Okay, so that's why VT will be same as that of the supply voltage. Alpha to pi, thyristor is in a conduction mode. Alpha to pi, thyristor is in a conduction mode. After pi, thyristor is in a conduction mode or off state. After pi, thyristor is in a conduction mode or off state. You can check the circuit operation. Pi, after pi, freewheeling diode is in a conduction mode. Na? So your thyristor will be in a off state, and we have written, yes, from, yes, during this interval, right? Pi to beta. What is VT? It is a minus Vs. That is a VT is negative. Okay. So VT is a negative. So this type of waveform will be getting. And after beta again, it is a minus Vs. Na? From beta to 2 pi, it is again minus Vs. So we'll be having this type of waveform. Let me draw it. So we'll be getting the waveform will be like this. Okay. And again, 2 pi to 2 pi plus alpha, same as that of the 0 to alpha, right? So we'll be getting this type of pulse. Is this clear? So alpha to pi only, thyristor is in a conduction mode. Pi to 2 pi, yes, it is a reverse voltage. And what is the peak value? It is a minus Vmax. So Pi will be your Vmax only, right? So can we draw the waveform for VDF, voltage across the freewheeling diode? Yes. Voltage across freewheeling diode waveform. Zero to alpha, alpha to pi, pi to beta, beta to 2 pi, right? 2 pi to 2 pi plus alpha. Come on. From 0 to alpha, what is the status of freewheeling diode? 0 to alpha, what is the voltage across freewheeling diode? Can anyone? Zero to alpha, freewheeling diode will be in the on state or off state? Off state. So what is the voltage across freewheeling diode? Come on. You can check the circuit. Yes, here it is. 0 to alpha, this is in off state, na? This is also in off state. Current is not flowing from source to load. So potential difference across the freewheeling diode is equal to potential difference across the load, na? Yes or no? Right? So what is the voltage across load? It is a 0 to alpha. So that's why your VDF also equal to 0, right? So VDF will be 0 from 0 to alpha. VDF will be 0 from 0 to alpha. From alpha to pi, what is VDF? From alpha to pi, what is VDF? Yes, alpha to pi, thyristor T will be in a conduction mode, na? So your freewheeling diode will be in an open state. So when thyristor T is in a conduction mode, what is the freewheeling diode voltage? It is a supply voltage, na? Yes or no? Right? But whether the supply voltage will appear as it is or reverse voltage will appear, you can check. Alpha to pi we are discussing supply voltage like a plus here, minus here. Na? Here it is plus, here it is minus supply voltage, right? So if it is plus here, if it is minus here, if thyristor T is in the conduction mode, and if we apply the KVL to this loop, na, it is like a plus Vs minus Vt plus VDF is equal to 0. In that Vt is a 0, na? Thyristor is in a conduction mode. So can I say that plus Vs plus VDF is equal to 0? So VDF is equal to minus Vs, right? So VDF is negative here. Okay, VDF is minus Vs. This will continue till pi. Okay, VDF is minus Vs. This will continue till pi. Okay. So this type of waveform will be getting. Means when thyristor is in a conduction mode, at that time your freewheeling diode will be in a reverse bias mode. Pi to beta, what is the freewheeling diode voltage? Pi to beta freewheeling diode is in a conduction mode, na? So pi to beta, this voltage is 0, right? Beta to 2 pi, come on, beta to 2 pi, what is the voltage across freewheeling diode? This is very simple. Beta to 2 pi, what is the voltage across freewheeling diode? Yes, it is a 0, right? Because beta to 2 pi, your load voltage is 0, na? If load voltage is 0, your voltage across freewheeling diode will be equal to 0. Beta to 2 pi, you can check. This is in off state, na? So voltage across load we are having it is a 0. So voltage across load is 0 means freewheeling diode voltage is also equal to 0, na? Right? So therefore it is a 0. So therefore beta to 2 pi it will be 0. After 2 pi again the same repeats. Whatever from 0 to alpha we are having, same will be from 2 pi to 2 pi plus alpha, and same goes on repeating. Is this clear? So what is the PIV rating here? V max is the PIV rating. Are you getting the point? Right? So this is the waveform for voltage across the freewheeling diode. Next, now let us derive the expressions. Yes, V0 average is equal to V0 waveform, same as that of the purely resistive load. Important thing. Now you can check the V0 waveform here. Yes, V0 waveform in this case RL load and freewheeling diode. And if you check the V0 waveform with a purely resistive load, we will be getting the same V0, na? In a purely resistive load also we are having this type of waveform V0, and in this RL load with freewheeling diode also we are having the same V0. Means here you can say that yeah, V0 average will be getting improved. Will be getting the improved V0 average, right? So let me write it as V0 average. It is a 1 by 2 pi integration from alpha to pi Vm into sine of omega t into d omega t, right? Vm into sine of omega t d omega t. So this can be written as Vm by 2 pi into integration of sine is minus cos of omega t alpha to pi. So this can be written as Vm by 2 pi into 1 plus cos alpha V0 average, right? V0 average. Okay. Next, I0 average will be like a V0 average by R. Okay. V0 average divided by R. Next, V0 RMS 1 by 2 pi integration from alpha to pi. Value is Vm square into sine square of omega t into d omega t, na, to the power 1 by 2. Right? If we simplify it, we'll be getting it as a Vm upon 2 root pi into, in bracket it is a pi minus alpha plus sine of 2 alpha divided by 2 to the power 1 by 2. Same as that of your purely resistive load. We have derived this expression in case of purely resistive load, right? So V0 RMS. Next, what is the conduction time of thyristor? Conduction time of thyristor. Thyristor is in on state from alpha to pi, na, right? So conduction angle is pi minus alpha. Conduction time is pi minus alpha by omega, right? Pi minus alpha divided by omega. This is the conduction time of thyristor. Okay. Next, what is the PIV rating of thyristor? PIV rating of thyristor. Yes, we have written. We are having the waveform for the voltage across thyristor, na? And in that yes, yes, you can check PIV rating is Vmax, right? So it is a Vmax. What is the circuit turn of time for thyristor? TC for thyristor. What is the circuit turn of time for thyristor? Yes, can anyone? What is the circuit turn of time for thyristor? Please check the instant at which current flowing through thyristor becomes 0. Current flowing through thyristor reaches 0 at yes, current flowing through thyristor becomes 0 at which instant? Current flowing through thyristor becomes 0 at which instant? At 180 degree. Yes or no? Right? That is at omega t is equal to pi. Current flowing through thyristor becomes 0. Right? So At beta, current flowing through thyristor is not reaching the zero. I am asking the current flowing through thyristor. At omega t is equal to beta, load current becomes zero. But current flowing through thyristor becomes zero at which instant? At omega t is equal to pi only, na? Because we are having thyristor is in a conduction mode only from alpha to pi. So at pi, current flowing through thyristor becomes zero. Yes or no? Right? And after that, till which instant the reverse voltage is maintained across thyristor? Till which instant the reverse voltage is maintained across thyristor? Yes, you can check this. At pi, actually the current flowing through thyristor reaches zero. And after that, the reverse voltage is maintained till 2 pi. So what is the circuit turn-off time? 2 pi minus pi by omega. Okay, 2 pi minus pi by omega. So it is equal to pi by omega. I am repeating. Your load current is non-zero from alpha to beta. But in alpha to beta, in that alpha to pi, thyristor is in a conduction mode. So load current is flowing through the thyristor from alpha to pi. And from pi to beta, freewheeling diode is in a conduction mode. So from pi to beta, yes, thyristor is in an off state. So current flowing through thyristor reaches zero value at omega t is equal to pi. Load current reaches zero value at omega t is equal to beta. Is this clear? Right? So that's why the circuit turn-off time for thyristor is a 2 pi minus pi by omega. So it is a pi by omega. Right? Next, what is the conduction time of freewheeling diode? Conduction time of freewheeling diode. Freewheeling diode is in on state from pi to beta, na? Right? So conduction angle is beta minus pi. And therefore conduction time is beta minus pi by omega. Okay? Beta minus pi divided by omega. Right? So conduction time of freewheeling diode is beta minus pi by omega. What is the PIV rating? PIV rating, yes, of freewheeling diode. FWD means freewheeling diode. Okay. What is the PIV rating of freewheeling diode? We are having the waveform for freewheeling diode voltage. What is the peak voltage? It is a V max, right? So it is a V max. Is this clear? Right? So this is about RL load and freewheeling diode. RL load and a freewheeling diode, right? Next, now we are going to discuss the RE load. We are going to discuss the RE load, right? So RE load means your battery charging circuit. Okay, battery charging circuit. So single phase half wave controlled rectifier with RE load, with the RE load. Okay, RE load, that is the battery charging circuit. So the circuit diagram. This is a VS, thyristor T, voltage across thyristor VT, IT, IS, R, E, V0 and I0. Okay, so the waveform Vs is equal to Vm into sine of omega t. Right? So, suppose the EMF E this is a EMF E. Okay, this is a Vs and this is a E. Next, get pulse to thyristor Ig. consider this as a theta 1. I'm considering this as a theta 1. This is a pi. Okay, so this will be like your pi minus theta 1. Okay. Suppose I am applying the get first to thyristor at this instant. This is your alpha. Okay. Let me write it as a theta alpha. This is like a pi minus theta. This is a pi 2 pi. Okay, this is a 2 pi plus theta. This is 2 pi plus alpha. Here it is a 3 pi minus theta and a 3 pi. Okay, so we're having these angles. Okay, very important. Please don't lose your concentration. Okay, they have asked the questions, right? RE load. So we're having the circuit diagram same as that of the previous case. The only thing is here we're having the load. In the load we're having a battery charging circuit, we can say. Okay, so this R is like a internal resistance of the battery, and E is nothing but the magnitude of that battery. Okay, so RE load. So you can check here. Vs is a Vm into sine of omega t. Okay, so Vs is equal to Vm into sine of omega t. So it is having a 0 to pi positive value, pi to 2 pi negative value, and so on. Right. Next, EMF E. The red indicates this red line. It indicates the magnitude of the EMF E. Okay, magnitude of the EMF E. Now let us discuss the status of this thyristor. Okay, means thyristor will be in which mode the thyristor will be operating, that we are going to discuss. So suppose when Vs is positive, it is like a polarity will be plus here and minus here, right? So when Vs is positive, here it is plus, here it is minus. So suppose if we consider here it is a 0 volt. If I consider negative terminal potential is 0 volt, what are the potential at this terminal? What is the function of this Vs to create a potential difference of Vs na? So positive terminal potential minus negative terminal potential, that should be equal to Vs. Negative terminal potential is 0 volt. So what is the positive terminal potential? Definitely it will be equal to Vs volt. Yes or no? So that's why the Vs minus 0, the difference will be Vs na, right? So if we consider this as a 0 volt, here it is a Vs volt. So what about the potential here? This is also equal to Vs volt. Okay, this is also equal to Vs volt. Next, this is 0 volt means here it is 0 volt only. This is 0 means here it is 0 volt. If this is 0 and here in between these two are having a E volt na, right? So negative plate potential of the E is 0. So what will the positive plate potential? It will be E na. So E minus 0 is equal to E, right? So now you can check. Initially it is like a thyristor is in an off state. Circuit will be at the rest position. So here potential is Vs, here it is a E. So if the circuit is at the rest position initially, thyristor is in an off state. What are the current flowing through the circuit? Current in the circuit is 0. Current flowing through the load, current flowing through the load is also 0. So what about the I0? 0. Voltage across resistor is a 0 na, right? So voltage across resistor is 0. So this is E, means definitely here it is a E. So that's why here it is a E. Are you getting the point? Voltage across resistor 0 volt means what? It indicates the potential difference across the two terminals of the resistor is equal to 0 volt, right? So if this is a E, therefore here it is E, here it is a E volt. So now you can check, yes, when Vs is positive, the potential at the anode is a plus Vs. right? It is a Vs means plus Vs na, and the potential at the cathode is E volt. Okay, so what is the potential difference or the voltage across the thyristor is a Vs minus E. Are you getting the point? Okay, Vs minus E. So now let me write it first. When Vs is positive, right? The potential at the anode of thyristor, right? Anode terminal potential is equal to plus Vs. Cathode potential is equal to minus E na, right? Sorry, E volt, not minus E. We have written it is a E volt, right? So it is a Vs here it is a E volt. Okay, so therefore voltage across thyristor is equal to Vt is equal to what? Anode voltage minus cathode voltage na, anode potential minus cathode potential. Anode potential is Vs, cathode potential is E, so that's why it is a Vs minus E. Yes or no? Vs minus E. Now please check this one. Now the meaning is, if Vs is less than E, our thyristor will be in a reverse bias mode. If Vs is greater than E, our thyristor will be in a forward bias mode. Yes or no? Right? Means whether thyristor is in a forward bias mode or not, it depends on the value of Vs and E. Are you getting the point, right? So let me write here. So as Vt is equal to Vs minus E. Okay, Vt is equal to Vs minus E. If yes, let me write, if Vs is less than E, Vt will be negative na, Vt will be negative. Means what? The thyristor T, yes, will be in a reverse bias mode. Thyristor T will be in a reverse bias mode. Okay, reverse bias mode. Next, if Vs is greater than E, Vt is a positive na. You can check Vs greater than E means it is a Vs greater than E means this difference will be positive. Okay, so therefore thyristor T will be in a forward bias mode. Okay, now you can check the waveform. Okay, so we are having the waveform for Vs and E. At omega t is equal to theta 1, Vs and E both are same. Before theta 1, what is happening? Vs is less than E. So for omega t is equal to 0 to theta 1, can we say that Vs is less than E? If Vs is less than E, the meaning is thyristor will be in thyristor will be in reverse bias mode. Yes or no? Thyristor will be in a reverse bias mode. So let me write it. Okay, for yes, or let me write here. Yes, for omega t is equal to 0 to theta 1. Omega t is equal to 0 to theta 1. What is happening? Vs is less than E. So therefore thyristor will be in which mode? Reverse bias mode. Right? Reverse bias. Okay. Next, from theta 1, from omega t is equal to theta 1 to, let us consider, yes, from theta 1 to till this instant. Okay, now you can check, I have written this as a pi minus theta 1. You can check at theta 1 what is happening. At theta 1, Vs and E both are same. At omega t is equal to theta 1, Vs and E both are same. Okay, so therefore can we say that between 0 to theta 1, whatever the angle we are having, means this angle is like a theta 1 we are having. Okay, this angle is like a theta 1. So again, can we say that from pi till this instant we are having again this same angle is theta 1. So that's why this angle is like pi minus theta 1. You can check sine 30 degree and sine 150 degree. Sine 30 degree and sine 150 degree, both values will be same only. Yes or no? Right? So means if this angle is theta 1, definitely angle between this instant and this instant is equal to theta 1 only. So this instant will be your pi minus theta 1, right? Because corresponding to this instant again, Vs and E both are same. Okay. So now from theta 1 till pi minus theta 1, you can check Vs is greater than E na, right? So from theta 1 till pi minus theta 1, Vs is greater than E. So for omega t is equal to theta 1 to pi minus theta 1. Omega t is equal to theta 1 to pi minus theta 1. Vs is greater than E. If Vs is greater than E means what? Thyristor T will be in which mode? Forward bias mode, na? Forward bias mode. Okay, thyristor T will be in forward bias mode. Is this clear? Right? Next, what will happen? Again, pi minus theta 1 to pi. Pi minus theta 1 to pi, again, Vs is less than E, na? So again, thyristor T will be in reverse bias mode. So pi minus theta 1 for omega T is equal to pi minus theta 1 to pi. Pi minus theta 1 to pi. It is like a Vs is again less than E. So thyristor T will be in a reverse bias mode. Reverse bias. Okay. So this is for omega T is 0 till pi we have discussed. After pi, what will happen? After pi, what will happen in the circuit? Yes, you can check after pi supply voltage is negative, na? After pi supply voltage is negative. So if supply voltage is negative means what? Yes, this here it is a minus, here it is a plus, right? So if this is minus, let me write here. Here it is a minus, here it is a plus. If I consider this as a 0 volt, this will be now, yes, if this terminal is 0 volt, then this terminal potential will be equal to minus Vs, na? Okay. Or let me, yes, draw this same diagram on the next slide. That will be good. Okay. Yes. Same I am drawing. This is a R and here it is a E. Vs, thyristor T. This is a Vt. Here it is a It, right? Here it is a Is. R and E. This voltage is V0. Okay. And this current is I0. Now, let us discuss for pi to 2 pi. Vs negative, na? So minus here, plus here. If I consider this potential is 0 volt, what about this potential? Positive terminal is 0 volt. Negative terminal will be minus Vs, na? You can check 0 minus of minus Vs is equal to plus Vs, na? So function of this voltage source is to create a potential difference. Positive terminal potential minus negative terminal potential should be equal to Vs volt. So if we consider this as a 0 volt, definitely this will be minus Vs. So this minus will appear here. This minus will be appearing here. So this is a minus Vs. This is 0 means again here it is a 0 volt. Here it is a 0 volt. Here it is a E volt, na? Same as that of the previous case. This is E means definitely here it is a E volt. Now you can check during, this is during pi to 2 pi. Yeah? This is during pi to 2 pi. Now you can check during pi to 2 pi, what is Vt we are getting? Vt is equal to minus Vs and this is anode voltage minus cathode voltage. Na? So Vt is equal to minus Vs minus E. So now you can check this is minus Vs minus E means what? The voltage across thyristor will be negative only, na? So whether can we say that during pi to 2 pi, during this interval, thyristor voltage will be negative. The meaning is thyristor will be in a reverse bias mode only. Are you getting the point? Right? So as Vt is negative, Vt is negative. So therefore, during omega T is equal to pi to 2 pi, omega T is equal to pi to 2 pi, thyristor T will be in a reverse bias mode only. Okay, reverse bias mode. Or you can say reverse blocking mode, because in the reverse bias we are having only one mode now, that is the reverse blocking mode. Is this clear? So till now we have discussed the during 0 to theta, Vs is less than E, thyristor reverse bias mode. 0 to theta 1 actually, theta means theta 1. Okay, during 0 to theta 1. Next you can check from theta 1 to pi minus theta 1, Vs is greater than E, thyristor is in a forward bias mode. Pi minus theta 1 to pi, Vs is less than E, thyristor is in a reverse bias mode. And from pi to 2 pi, from pi to 2 pi, yes, voltage across thyristor is a negative only, na? It is a minus Vs minus E. So that's why your thyristor will be in a reverse blocking mode only, or a reverse bias mode only. Okay. So now you can check out of these intervals 0 to theta 1 to pi minus theta 1, pi minus theta 1 to pi, and pi to 2 pi. Okay, out of these intervals, only during theta 1 to pi minus theta 1, our thyristor is in forward bias mode, right? Only during pi minus theta 1 to only during theta 1 to pi minus theta 1, thyristor is in a forward bias mode. So we need to apply the gate pulse only during this interval, na? Theta 1 to pi minus theta 1. If I apply, suppose if I apply the gate pulse to the thyristor for omega t less than theta 1, suppose if I apply the gate pulse to thyristor for omega t less than theta 1, whether our thyristor will turn on? Suppose instead of applying the gate pulse here, I am applying the gate pulse at this instant, whether our thyristor will turn on? Yes, no? Thyristor will not turn on, right? Thyristor will not turn on. Is this clear? Okay, so thyristor will not turn on, right? Anonymous attendee. Okay, sir, solve questions. Please don't tell me when to solve the questions, right? Let me complete it. Single phase half wave control rectifier. After that, we'll discuss the questions. Okay. Yes. Please don't give the suggestions. Right. So here, for if alpha is less than theta 1, if alpha is less than theta 1, thyristor, if alpha is less than theta 1, thyristor will be in a reverse bias mode. So even though if we apply the gate pulse, our thyristor will not turn on. So the point is we need to apply the gate pulse only after theta 1. Na? We need to apply the gate pulse only after theta 1. We need to apply the gate pulse only after theta 1. Is this clear? Right? So alpha should be greater than theta 1. Alpha should be greater than theta 1. Right? So that's why we applied the gate pulse at this instant. Okay. So now my question is, during theta 1 to alpha, what will be the mode of operation of thyristor? I'm saying from theta 1 to alpha, what will be the mode of operation of a thyristor? Yes. Theta 1 to alpha, thyristor will be in. Yes, very good. Forward blocking mode, na? Thyristor will be in a forward blocking mode, right? Thyristor will be in a forward blocking mode. Is this clear? Right? Means after theta 1, thyristor will be in a forward bias mode. But till alpha, we have not applied the gate signal. So that's why from theta 1 to alpha, thyristor will be in a forward blocking mode. Okay. So now at alpha, we are applying the gate signal. At alpha, we are applying the gate signal, right? So now let us discuss the circuit operation for different intervals. Okay. Circuit operation for different intervals. This is the thing, whatever we discussed till now is only how to, yes, in order to identify whether in which interval thyristor will be in a forward bias mode and in which interval thyristor will be in a reverse bias mode. That thing only we have identified. Okay. Now let us discuss the circuit operation. So first, for omega t is equal to 0 to theta 1. This is theta 1. So let me consider it as theta 1 here. This is also theta 1 here, and this is also theta 1. Okay. So now, yes, for omega t is equal to 0 to theta 1. For omega t is equal to 0 to theta 1. For omega t is equal to 0 to theta 1. Yes. For omega t is equal to 0 to theta 1. Yes. What is Vs? Vs is less than E. Vs less than E means thyristor will be in which mode? Thyristor will be in, yes, reverse bias mode now, right? So we'll be having reverse bias means thyristor will be in off state only. Yes or no? This is a Vs. Okay. This is a Vt, It, Is. Okay. Is, It. This is a Vs. Vs is positive na, 0 to theta 1. So this is a positive. This is a E. Here it is a R. This is a V0 and here it is a I0. Now we can check thyristor is in reverse bias mode. Okay, that is nothing but reverse blocking mode. Okay. So thyristor T will be in reverse blocking mode. Reverse blocking mode, right? So thyristor is in a reverse blocking mode means what it is like in off state. So whether the current will flow from source to the load? No, current will not flow from source to the load. Okay. So what is I0 here? I0 is equal to 0 ampere. What is the V0 in this case? Come on. What is the V0 now? Yes, V0. 0. No. E. Yes. Some are saying E. Correct. Yes. So V0 means what? Potential difference between these 2 points. Na? V0 means potential difference between these 2 points. So you can check V0 means what? I0 into R plus E. I0 is 0. But what about the V0? V0 should be equal to E only. Okay. So let me write it as V0 is equal to E. So here V0 is equal to E and I0 is equal to 0 ampere. Okay. I0 0, V0 E. Right. Next, what about the VT here? Can we apply KVL to this loop? Yes, KVL to loop. So it is like a plus Vs minus Vt minus V0 is equal to 0. Out of that, V0 is a E, na? Right? So therefore, Vt is equal to Vs minus E. Vt is equal to Vs minus E. This is from 0 to theta 1 only. Right? Vs minus E. Next. So during 0 to theta 1, we can draw the waveform V0 and I0. Vt waveform we will draw at the end. Okay. So 0 to theta 1, V0 and I0 both will be 0. Okay, both will be 0. Theta 1 to alpha, from omega t is equal to theta 1 to alpha, what will happen? So for omega t is equal to theta 1 to alpha. For omega t is equal to theta 1 to alpha. So theta 1 to alpha means thyristor is in a forward bias mode, but we have not applied the gate signal, na? So thyristor will be in forward blocking mode, right? So here Vs is greater than E. Vs is greater than E. Okay, but we have not applied the gate signal. So waveform or the equivalent circuit will be like this. Thyristor will be in a forward blocking mode. This is a Vs plus minus Vt, It, Is, R, E, V0, and here it is I0, right? So you can check here, thyristor will be in forward blocking mode. Forward blocking mode. Okay. Next, what is the V0 now? V0 is again E, na, because current is not flowing. So I0 is equal to 0 ampere. V0 is equal to E volt. V0 is equal to E, I0 is 0, right? Vt, apply KVL to the loop. Okay. KVL to loop. So it is like a plus Vs minus Vt minus V0 is equal to 0. So therefore Vt is equal to Vs minus V0, but V0 is E, na? So that's why it is a Vs minus E. But as Vs is a greater than E, so that's why your Vt will be positive now. Vt will be positive. But before theta 1, it is like a Vt will be negative. Okay, we are going to draw the waveform of Vt. Okay, next. Alpha till pi minus theta 1. Please check. Alpha till pi minus theta 1, what will happen? For omega t is equal to alpha, from alpha means this instant. Okay, this is alpha. Alpha till pi minus theta 1, Vs is greater than E, and we have applied the gate signal, na? So that's our thyristor will be in a conduction mode. Okay, thyristor will be in a conduction mode. So let me draw the circuit. For omega t is equal to alpha to pi minus theta 1. Omega t is equal to alpha to pi minus theta 1. Yes, supply voltage Vs. Thyristor will be in conduction mode. Okay, because we applied the gate signal R E. So this is the Vs plus minus. This is the Vt, It, Is, right? R E. This is a V0, and here it is a I0, no? V0 and I0, right? Now you can check in this circuit. Okay, thyristor is in which mode? Forward conduction mode. Forward conduction mode. Thyristor is in a forward conduction mode, right? Now, so Vt will be 0. Vt will be 0. What about the V0? Can we apply KVL to the loop? Yes, KVL to loop plus Vs minus Vt minus V0 is equal to 0. So out of that Vt is 0 na, so therefore V0 is equal to Vs, means what? V0 is same as that of the supply voltage. Okay, V0 is same as that of the supply voltage. Now V0 is same as that of supply voltage, so what is the I0? Yes, I0, can we write? Yes, V0, further we can write V0 is equal to I0 into R plus E. I am applying KVL to this part only, plus V0 minus I0 or minus E. So that's why V0 is equal to I0 or plus E, right? So therefore I0 is equal to V0 minus E divided by R, which is nothing but Vs minus E divided by R. This is your I0, Vs minus E by R, right? Vt 0, V0 Vs, I0 is Vs minus E by R. So let us draw the waveform during this interval. Yes. You can check theta 1 to alpha again, I0 0, V0 was 0, right? Sorry. V0 was not 0, V0 was E actually, sorry. 0 to theta 1 to alpha. V0 was E now we have written. Yes, 0 to theta 1, V0 is E. Theta 1 to alpha, V0 is E. Okay, correct. So let me indicate it as here. So this is E, this is E. Okay, V0 is E, right? Next, and I0 is yes 0. I0 is 0. After alpha, what is happening? After alpha, V0 is from alpha to pi minus theta 1. Just now we written alpha to pi minus theta 1. V0 is same as that of the supply voltage na. So if V0 is same as that of the supply voltage, so you can check at alpha. This is alpha na. So if you check here, yes. So if you check here, this is the alpha instant we are having. Okay. So corresponding to this instant, we are having the Vs is here. This is equal to Vm sin alpha na. This is your Vm sin alpha. And till alpha, we had a V0 is equal to E, means V0 was here actually. And at alpha, it will sudden increase to Vs value, means what? V0 will sudden increase from E to the Vm sin alpha, means V0 will be like this. From E to the Vm sin alpha, it will change. From E to the Vm sin alpha, it will change. Are you getting the point? Previously, it was E. At alpha, it will suddenly increase to the Vm sin alpha. Vm sin alpha means what? Value of the supply voltage at omega t is equal to alpha. Value of supply voltage at omega t is equal to alpha, right? Next, alpha to pi minus theta 1. Alpha to pi minus theta 1. Yes, we are having V0 is same as the supply voltage. So you can check from alpha to pi minus theta 1. Yes, V0 is same as the supply voltage. Supply voltage is like this. So that's why here we will be getting this type of pulse. Okay, this is a Vs only. This is a Vs only, right? And what about the I0? I0 you can check is equal to Vs minus E by R. I0 is Vs minus E by R. The meaning is I0 at alpha it was a 0. Means till alpha it was a 0. At alpha it will be like a Vs minus E by R. So you can check at alpha Vs is this value. E means this value. So the difference is Vs minus E. The difference is a non-zero, right? And divided by R means what? Your I0 will increase suddenly to, yes, at alpha. And after that, what will happen? It is a Vs minus E by R. So it will be having the shape like this. At pi minus theta, Vs and E both are same na. So that's why it will be like this. Okay, it will be like this. Are you getting the point? This is a V0 red one, and this one is a I0. This one is a I0. Blue one is a I0, right? So this will continue till pi minus theta 1. Pi minus theta 1. Next, pi minus theta 1 to pi. From pi minus theta 1 to pi, what will happen? For omega t is equal to pi minus theta 1 to pi. Pi minus theta 1 to pi, Vs is less than E na. Thyristor will be in a reverse bias mode now. Thyristor will be in a reverse bias mode. So thyristor will be in an off state. So this is a R, this is a E, this is a V0, and here it is a I0, VT, Vs, right? Vs is positive only, na? Pi minus theta 1 to pi. So Vs is positive. Okay. This is your Is. This is the IT. So thyristor mode of operation, reverse blocking mode. Thyristor will be in a reverse blocking mode. Reverse blocking mode. Right. So now you can check here. What is a V0? V0 is equal to E. I0, 0 ampere. Okay. Because open circuit. What is a VT? VT is equal to, you can apply KVL, plus Vs minus VT minus V0. So it is a Vs minus E actually. VT is equal to Vs minus E. We'll be getting, right? Next. So this is from pi minus theta 1 to pi. V0 E and I0 0. So it will be V0 is a E and I0 is a, yes, V0 is a E and I0 is a 0. I0 is a 0. This type of waveform. And pi to 2 pi, what will happen? From omega t is equal to pi to 2 pi. For omega t is equal to pi to 2 pi. It is like supply voltage reverse, na? Thyristor will be in reverse blocking mode now. Vs minus plus. This is Vt. This is R, E, V0 and I0, right? This is the IT. Okay. So thyristor T will be in reverse blocking mode. Reverse blocking mode. So here V0 is equal to E only, na? Current is not flowing in the circuit. I0 is equal to 0, right? What is VT? Apply KVL. KVL to loop. We'll be getting it as a minus Vs minus Vt minus V0 is equal to 0. So therefore Vt is equal to minus Vs minus V0. But V0 is a E, na? So we can write it as minus Vs minus E. This is a Vt. So you can check V0 is E, I0 is 0. So the waveform will be like this. V0 is a E volt till 2 pi, right? And I0 is equal to 0. This type of waveform we're getting. And after 2 pi, again the same cycle repeats. Okay. So again, this is a E. Again, the same waveforms will be getting. And for in current, this will be like this shape. Okay. So this is I0 and this one is your V0. This one is V, right? So this is the circuit operation. So you can check here, current is flowing in the circuit only from alpha to pi minus theta 1. Okay, right? So, and for remaining part, it is like a thyristor is in an off state only. For remaining intervals, thyristor will be in an off state only, right? Now, can we derive the expressions? V0 average, yes, I0 average, okay, V0 RMS, I0 RMS, right, and so on. So let us derive the expressions. V0 average. You can check the V0 waveform. Yes, this is the V0 waveform. So V0 average expression either we can derive by first finding the I0 average, and after that V0 average we can find, or from this V0 waveform also we can find the V0 average. In both the ways I will tell you. If we first find the I0 average expression, then it will be a bit lesser time consuming. Okay, but in both the ways I will tell you. So V0 average, you can check the V0 waveform during from 0 to 2 pi, whatever the waveform we're having, the same is repeating from 2 pi to 4 pi, right? So you can check here 1 by 2 pi. 1 by 2 pi. In that integration, we're having the three parts. Na? One is a 0 to alpha. 0 to alpha. During 0 to alpha, what is the V0? It is a E into d omega t plus integration from alpha to pi minus theta 1. Pi minus theta 1. Okay. So during this interval, it is a same as that of the supply voltage. Vm into sine of omega t into d omega t plus third interval is from pi minus theta 1 to 2 pi, right? The value is e again, e into d omega t. Okay, so this is the expression. We can simplify it. Okay, no need to simplify here at the time of numerical discussion. Okay, we will simplify it. Okay, if requires, right? So is this clear? Next, I0 average. I0 average. If you check the I0 waveform, yes, this is the I0 waveform. You can check whatever the waveform varying from 0 to 2 pi, the same is repeating from 2 pi to 4 pi. And in that also the effective interval is non-zero interval is from alpha to pi minus theta 1 only. Okay, alpha to pi minus theta 1 only. So let me write it as 1 by 2 pi integration from alpha to pi minus theta 1. During this interval alpha to pi minus theta 1, what is the value of I0? It is a Vs minus E by R, na? Right? So it is a Vs means Vm into sine of omega t minus E divided by R. Okay, into d omega t. Okay, so this is the I0 average. Now once we get the I0 average, from this also we can find the V0 average. Let me tell you how to find. Okay, we know V0 is equal to what? I0 into R plus E, na? Because load is RE load. V0 is equal to I0 into R plus E. What is the average value of this E? What is the average value of this E? E only, na? Because E is a constant. So that's why average will be E only. Okay. So average of E is equal to E only. So therefore, can we write V0 average is equal to I0 average into R plus E only. So from this I can write, yes, I0 average, suppose we have calculated I0 average by using this expression, and then we can put that I0 average here and we can find the V0 average, right? So why I'm telling this? Because you can check in the V0 average, we require to simplify 3 intervals, na, 3 integrations. But whereas in order to find the I0 average, we need to simplify only 1 integration. So this will save the time, na? I0 average, finding the I0 average first, this will save your time. Okay, so that's why by using this I0 average, you can find the V0 average. Okay, by using this expression, right? Next, V0 RMS. V0 RMS is equal to 1 by 2 pi. Okay, integration, we are having the 3 intervals. Integration from 0 to alpha, it is a E square, na? Because V0 is E, plus integration from alpha to pi minus theta 1. During this interval, it is the same as that of the supply voltage. So it is a Vm square into sine square of omega t into d omega t, plus integration from pi minus theta 1 to 2 pi. It is a E square into d omega t to the power 1 by 2, right? This is a V0 RMS. No need to simplify here. Okay, so please try to understand only thing. RMS means what? Square root of mean of squared value, no? So we have squared the V0 values during the respective intervals, and again we have taken the average and again put it into the square root. This is a V0 RMS, right? Similarly, we can find the I0 RMS. I0 RMS is equal to 1 by 2 pi integration from, for I0, the non-zero interval is from alpha to pi minus theta 1, na? Alpha to pi minus theta 1, alpha to pi minus theta 1. During this interval, what is I0? Vs minus E by R. So what is Vs? Vm into sine of omega t minus E divided by R, bracket square into d omega t to the power 1 by 2. Right? To the power 1 by 2. Right? Square root of mean of squared value, na? Vm sin omega t minus E by R, bracket square. Right? So this is I0 RMS. Next, what is the load power? Load power, which is equal to P0 average. Come on. In the load, we are having a resistor and a EMF, na? So how to find the load power? Yes, P0 average is equal to I0 RMS square into R plus I0 average into E. Please, you can check in the case of piecewise modeling of the devices also, na, we are having one purely resistor, that is a MOSFET, is represented as a resistance, BJT as a constant voltage source, okay, and third one is a V, that is the voltage and a resistor combination. In that also, what was the power loss? Yes, the same power loss, okay, the same expression we are going to use here. Is this clear? In the case of resistor, we know power loss is equal to I0 RMS square into R, and E is your constant now. If E is a constant, so therefore your power consumed by the E is nothing but average power consumed by the E. I am saying only E here. Average power consumed by the E is nothing but E into I0 average. Okay, so this is the expression for your load power. V I0 RMS square into R plus E into I0 average. This is only for RE load. This is only for RE load, right? Next, what is the conduction time of thyristor? Conduction time of thyristor. Yes, thyristor is in on state from alpha to pi minus theta 1, na? Right? Only alpha to pi minus theta 1. So it is like a pi minus theta 1 minus alpha divided by omega, na? Pi minus theta 1 minus alpha divided by omega. This is the conduction time of thyristor, right? Next, so what is the PIV rating and what is the circuit turn-off time? We'll discuss it after drawing the VT waveform. Okay, VT waveform we need to draw first. Okay, so next, so yeah, can we find the input power factor? Input power factor. Yes, if you check the circuitry, in the circuit we are having source and a load, that is a battery charging, okay, and in between we are having only switch, na, and that switch is a lossless switch, ideal switch we are having. So can we say that supply power is equal to load power? Yes, so we can write source power is equal to load power. What is the source power? Vs RMS into Is RMS into cos phi s, which is equal to load power is P0 average. So therefore you can write cos phi s is equal to P0 average. Just now we have written it is a I0 RMS square into R plus I0 average into E, na, divided by Vs RMS into Is RMS. This is the expression for your input power factor. Cos phi s is nothing but input power factor. Input power factor. Okay, so this is the input power factor. Next, now can we draw the waveform for VT, voltage across thyristor? Okay, voltage across thyristor. Let us draw. We're having the intervals like 0 to theta 1, yes, omega t 0. We're having the intervals like 0 to theta 1, right? Theta 1 to alpha, alpha to pi minus theta 1, pi minus theta 1 to pi, right? Pi to 2 pi, or let me write pi to pi plus theta 1 also. Here it is a 2 pi minus theta 1. Let me write. And next, same. Okay. So during 0 to theta 1, during 0 to theta 1, yes. Suppose this is the E. Right? During omega t is equal to 0 to theta 1, what is the VT? we have written during 0 to theta 1 Vt we are having. Yes, in this 0 to theta 1 you can check. Yes, 0 to theta 1. What is Vt? Vs minus E na. So during 0 to theta 1, it is a Vs minus E. So whether Vs is less than E or greater than E during 0 to theta 1. During 0 to theta 1, Vs is less than E na. So Vs minus E difference will be positive or negative. It will be negative only. You can check at omega t is equal to 0, Vs is 0. So Vs minus E difference will be like a 0 minus E. So that's why at omega t is equal to 0, your voltage across thyristor will be equal to minus E. After that, you can check. After that, from 0, as we are moving towards the theta 1 na. From 0, as we are moving towards the theta 1, your Vs value is increasing. If Vs value is increasing, Vs minus E difference decreases. At theta 1, at omega t is equal to theta 1, Vs and E both are same na. So if Vs and E both are same, so what is Vs minus E? It will be 0. So please try to understand. Yes, between omega t is equal to 0 to theta 1, the waveform for Vt, it will be like this. Let me use the different color. Yes. Here it is a minus E. It is starting from minus E because at omega t is 0, Vt is equal to Vs minus E. At omega t 0, Vs is 0. So it is a 0 minus E means what? Minus E. So that's why it is starting from minus E. After 0 till theta 1, as omega t increases, as omega t increases, Vs increases. So Vs minus E difference decreases. So that's why it is a decreasing. At theta 1, Vs is equal to E. So Vs is equal to E means what? It is a 0. Vs minus E will be 0. So that's why it is a 0. This will be till your 0 to theta 1. From theta 1 to alpha, you can check from theta 1 to alpha what is happening. From theta 1 to alpha, Vs is greater than E na. So what is the difference? Vs minus E, that will be positive. Okay, right? Vs minus E difference will be positive. So theta 1 to alpha, the Vs minus E will be positive. Right? At alpha, we are applying the gate signal. So thyristor is turning on na. So voltage across thyristor will be 0. Right? Next, alpha till pi minus theta 1, thyristor is in on state only. So voltage across thyristor will be 0 only. Yes or no? From pi minus theta 1 to pi, from pi minus theta 1 to pi, what is happening? You can check. From pi minus theta 1 to pi minus theta 1 to pi, again Vs is positive only. Thyristor is in an off state. So voltage across thyristor is again Vs minus E. So Vs is less than E na. From pi minus theta 1 to pi, Vs is less than E. So Vs minus E difference will be negative. Right? At omega t is equal to pi, Vs is a 0. So what is Vs minus E? Vs minus E will be minus E. Okay, Vs minus E will be minus E. So the waveform will be like this. Pi minus theta 1 to pi, it will be just like this. At pi, it is reaching minus E because at pi supply voltage is 0 na, right? Next, after pi, what will happen? After omega t is equal to pi, what will happen? Let us discuss. Okay, so after pi, you can check supply voltage is negative na. After pi, supply voltage is negative means it is like a yes minus here and here it is a plus. Okay, so if this is minus, this is plus means here it was a minus Vs na. We have written yes. Yes, here we have indicated. If Vs is negative pi to 2 pi, it is a minus Vs, it is a E na. So it is voltage is minus Vs minus E means what? Addition of these two waveforms. This is negative and this negative minus this. So that's why total will be getting added and resultant will be your negative. Okay, this will be continuing till, yes, you can check till this instant, 2 pi plus theta 1, till 2 pi plus theta 1. Let me show you. This is a 2 pi and this is a 2 pi plus theta 1, suppose. So the waveform will be like this. Okay, and after that again the same cycle repeats. Okay, so this peak value is nothing but your Vm plus E, maximum value of the supply voltage plus EMF. Okay, this is your peak inverse voltage in this case. right? You can check. This is Vs minus E. This indicates minus Vs minus E. Okay, minus Vs minus E. So that's why it is. It is like a addition of negative terms, right? So that's why it is a greater than that of your E, right? Peak value of the supply is Vm and E is constant. So that's why it is a Vm plus E we are getting here, right? Next. So two terms remaining we need to find. One is the circuit turn-off time for thyristor and a PIV rating. So let us first find PIV rating. PIV rating of thyristor. PIV rating of thyristor T. Yes, it is a Vm plus E. Vm plus E. Okay. And next, what is the circuit turn-off time? TC for thyristor. TC for thyristor T. Yes, what is the TC? Can anyone? TC for thyristor. Current flowing through thyristor becomes 0 at pi minus theta 1. And after that, the reverse voltage is maintained till 2 pi plus theta 1. 2 pi plus theta 1. Means after pi, after 2 pi, right? This is a 2 pi now we are having. Okay, this is a 2 pi. So after 2 pi, the waveform will be same as that of your 0 to this alpha waveform, na? 0 to alpha waveform. So you can check 2 pi to 2 pi plus theta 1 means this is theta 1. So this whatever the pulse we are having, same is, yes, here we are having from 2 pi to 2 pi plus theta 1. Right? So you can check circuit turn-off time. It is a 2 pi plus theta 1 minus pi minus theta 1 divided by omega. 2 pi plus theta 1 in bracket minus pi minus theta 1 divided by omega. So it is equal to 2 pi minus pi, that is a pi plus 2 theta 1 divided by omega. Okay, this is the TC for thyristor T. Circuit turn-off time. One more last thing. How to find theta 1? That is also important, na? How to find theta 1? Because you can check at theta 1, Vs and E both are same. Okay, so let me write at omega t is equal to theta 1. Vs is equal to E. Yes or no? And what is Vs? Vs is a Vm into sine of theta 1. At theta 1, at omega t theta 1, Vs is equal to Vm sine theta 1, na? Which is equal to E. So therefore, from this we can write theta 1 is equal to sine inverse of E upon V max. Sine inverse of E upon V max. This is your theta 1, right? Okay. So stop here. This is about the circuit analysis for RE load. Okay, most complicated RE load. Even compared to that of RLE load, RE load is the most complicated. Okay, so please go through it once, watch the video, go through the class notes. Okay, and before coming, okay, for the tomorrow's session, please read each and everything whatever we have discussed in the yesterday's session as well as today's session. Otherwise, most difficult circuitries will be coming here. Okay, tomorrow. Yet we have not discussed about the full wave control rectifier. Again, we will be having the Fourier series analysis and the three-phase circuit analysis also, or the three-phase rectifiers also. Okay, so yes. Now you are having, if you are having any doubt, please ask.
Sir,
Yes, please.
sir, in RL load with the freewheeling diode, sir.
In RL load with freewheeling diode, do you know the slide number?
No, sir, I didn't note that.
Okay, just a minute. Yes, here.
Sir, here you told theta means up to theta, inductor will be DIL by dt will be positive. That is, inductor will store the energy. After theta, it will release the energy, sir. While releasing, it will release to diode. But here you said diode will be on only from pi. How, sir? It need to be on, diode need to be on from theta itself. No, sir, because from theta itself it starts discharging.
I will tell you. Okay. Alpha to theta, thyristor will be in a conduction mode. Is that okay?
Yes, sir.
Inductor stores energy.
Yes, sir.
Right. Next, after theta, what is happening? Please check. Okay. Means let us consider from theta to pi. Okay. So from theta to pi, if you check, VDF means what? Voltage across diode.
Yes, sir.
Which is equal to, can we say that, or can we apply KVL to this part only?
Yes, sir, we can apply.
If I apply KVL, it is like a minus VDF, minus VR, minus VL.
Okay, sir. At the time, yes, sir, it is, sir.
Just a minute. I will write first. Okay. Okay. Here I will add the page. Yes. So you can check here during omega t is equal to theta to pi. You are having the doubt, na?
Yes, sir.
So during theta to pi, can we write minus VDF minus VR minus VL is equal to 0?
Yes, sir.
Next, what is VDF? Is equal to minus VR
Minus
minus
V0.
VL.
Yes, sir.
Okay. Now you can check after theta, it is like our inductor voltage is negative, na?
Yes, sir.
So if this is negative, the meaning is it is equal to minus VR. Minus of minus means it is like a VL. VL
Okay,
is
sir.
already negative.
Okay, sir.
Now let me finish first. So VDF is like VL minus VR. Now if VL is less than VR, then it is like a freewheeling diode will be in an off state.
Yes, sir.
Okay, then freewheeling diode will be in an off state. And if VL is greater than VR, freewheeling diode will be in an on state.
Yes, sir.
Now you can check the waveform. This is the thing first. If VL magnitude is less than VR, then freewheeling diode will be in an off state. If VL is greater than VR, freewheeling diode will be in an on state. Right?
That only, sir. After theta, the inductor start discharging, sir.
After theta, inductor starts discharging.
The discharged current will be flowed through source and thyristor, sir.
Yes. From theta to pi, inductor is we cannot say the inductor charges or discharges. Let us use the proper words. Inductor stores energy and releases energy.
Okay, sir.
Okay, so from theta to pi, actually the inductor is releasing the energy through supply and the thyristor.
That's only my doubt, sir. Yes, sir. Okay, sir. Okay, sir.
Is this okay?
Yes, sir. That's it, sir. Thank you, sir.
Okay. Yes. Yes, next.
Sir,
Yes, please.
we are writing expression for TC as pi minus theta by omega something, no sir? I mean,
For
in that
which
manner.
you are saying?
Turn off time, sir. Circuit turn off time.
Which circuit? Circuit turn off time but for which circuit you are saying?
For anything, I'm telling generalized way, sir.
Okay.
For example, for the last circuit, RE load,
Okay.
we have written pi plus 2 theta by omega, no sir?
2 pi plus theta 1 minus pi minus theta something. Okay, divided by omega. Yes.
Okay, sir. We are calculating TC, that means time. And we are writing in terms of pi plus 2 theta means that gives angle. And again, omega means 2 pi f. There is a somewhat confusion, sir. Can you?
No. The thing is, please listen. If you check the waveforms, we are having the x-axis means omega t.
Yes, sir.
Omega is your radian per second.
Yes, sir.
And t is the time.
Yes, sir.
So if omega t is your angle, na?
Yes, sir.
So if omega t is the angle, so if I take the difference of the two angles, means the resultant is angle only. And again, if I divide that angle to the omega,
now omega t by omega again t. Okay.
Right? Omega means we are dividing with the omega, na? So that's why we are getting time.
Okay, sir. Okay.
Is this clear?
Yes, sir. Clear, sir.
Right.
Hello, sir.
Yes, please.
Sir, in the last RL load, sir, RE load, sir, the conduction.
RE load. Yes, in the RE load.
Yes, sir. Conduction time of thyristor, we have not taken.
Conduction time of thyristor, we have not calculated.
Sir, the last load we have taken, sir, today.
This is na conduction time of thyristor we have calculated.
Sir, in last load we have calculated.
Last means RE you are saying?
Yes, sir. Yes, sir.
This is RE only.
Okay, sir.
Right? Okay.
Hello, sir.
Yes, please.
Sir, RL load, how we are drawing the waveform of VR?
VR. Okay. Please listen. VR means voltage across resistor,
Yes, sir.
right? So according to Ohm's law, what is voltage across resistor? I into R.
Yes, sir. All right.
Which current is flowing through resistor? Resistor is a load branch, na?
Yes, sir. I note only.
Current flowing through resistor is I0.
Yes, sir.
So if we are having the I0 waveform, can we draw the waveform of VR?
Yes, sir.
So from
Sir,
I0 we
means-
are drawing the waveform of VR. Yes.
सर मीन्स जैसे अगर लोड RL है या RL ही है कैसा भी है, जैसी भी वेव फॉर्म आई नोट की होगी वैसी VR की होगी हमेशा, बाकी कंपोनेंट्स की अलग हो सकती है.
कौन से लोड में आप बोल रहे हैं? कौन से लोड में बोल रहे हैं आप?
सर लोड मतलब जैसे RL है या RLE है या कोई भी है जिसमें R और उसके अंदर फ्लो होने वाली करंट है हमारे पास, तो जो वेव फॉर्म
yes.
करंट की होगी वही VR की होगी हर लोड में.
हाँ, yes, yes. VR की वेवफॉर्म जो करंट की है वही होगी.
ओके ओके, थैंक यू सर.
Okay. Okay. हाँ. Yes, please. Hello.
Hello, sir.
हाँ, please one by one. हाँ, yes.
Sir, in RL load, sir, will you please explain?
Avinash, please. हाँ.
Sir, in RL load, will you please explain the interval from theta to pi, sir? Once.
Theta to pi in RL load.
Yes, sir.
RL or RL with freewheeling diode?
Sir, RL load.
Pure only RL without freewheeling diode, na?
Yes.
Okay. Okay. Yes, yes. Theta to pi.
Yes, sir. Theta to pi. Sir, waveform.
You want waveform?
Yes, sir.
Okay, just a minute. Theta to pi. Okay.
Yes. Sir.
Yes. Here it is RL load.
Yes.
So you can check what is happening in this circuit. First thing is from alpha till theta, inductor is storing the energy.
Yes.
After theta, what is happening? Inductor is releasing the energy,
Yes, sir.
right? Because VL is a negative, na?
Yes, sir.
So that's why inductor releases when inductor releases energy through the thyristor, na? Because inductor is not having another part to release the energy. Only one loop we are having.
Yes, sir.
So inductor releases the energy through supply and the thyristor.
Yes, sir.
So what is the V0? Same as the supply voltage because thyristor is in a conduction mode.
Sir, inductor
Right?
will. Yes. Sir.
Are you getting the point?
Yes, sir. Yes.
Thyristor is in a conduction mode, right? Due to
Yes.
that, V0 is equal to Vs only. So here theta to pi, V0 is equal to Vs only. And I0 is decreasing. Why the I0 is decreasing? Because your VL is negative, na? Means inductor
Yes.
is releasing the energy,
Yes, sir.
right?
Yes, sir.
Okay.
Sir,
And sir, this theta we have considered that before theta the inductor is charging and after theta it is discharging.
Please don't use the word that charging. It is a storing energy.
Yes, sir. Storing energy.
Charging, discharging, we are having concept in the capacitor.
Yes.
In inductor, we don't have the charging and discharging concept. Okay, it is a storing energy and releasing energy.
Okay, sir. Sir, what we consider means theta. Then,
And what? Please repeat.
sir, the theta instant what we have to consider in the waveform means before theta the inductor stores energy and after theta it releases energy. That
Yes. At theta, what is happening? You can check at theta what is VL. At theta, VL is 0, na?
0. Yes, sir.
So it is like a boundary between inductor stores energy and inductor releases energy.
Yes. And sir, its value is near to pi. Exact means or approximately pi, sir.
No, it is near to pi.
Okay, sir.
It is definitely less than pi. It is not equal to pi. It is less than pi only. Right? Okay.
Sir,
Yes, please.
sir, from in this page only, sir, from from theta to pi, the inductor releasing energy, no, sir.
From theta to pi, inductor releases energy. Yes.
After pi to beta, that means it is reverse voltage, no, sir.
So
switch will be open, no, sir.
okay. No. Means you are having doubt from pi to beta, na?
Yes, sir.
Okay. Theta to pi inductor releases the energy, but you can check from theta to pi. It is not like that inductor energy becomes zero. It is not like inductor has energy. Inductor has released the energy fully. It is not like from theta to pi. Means till pi also inductor is having some energy to release.
Okay.
Okay, means after pi also inductor will continue go on releasing the energy in opposition to that of the supply voltage. Means even though the supply voltage is negative na, but then
Yes,
also our thyristor will be in a forward conduction mode only. I am using the word forward conduction mode. The meaning is from pi to beta, thyristor will be in a forward bias mode only. Why I am saying that? Because you can check here, the thyristor voltage waveform means what waveform not we are having, but we can say the magnitudes. This vertical red lines are now we are having.
Yes, sir.
Yes, these vertical red lines means it indicates the magnitude of the VL. Right?
Okay.
So you can check near to the pi, what is the VS you can consider this one. Huh? Near to the pi means suppose this instant. Let me use the different color. Yes, that will be good. Near to the pi, VS is only this value now we are having.
Yes, sir.
Suppose this value. Let us consider this is a VS. Okay. VS is only this much. And what about the VS corresponding, VL corresponding to this instant? VL is from this point to this point we are having.
Yes, sir.
So whether VL is greater than VS or less than VS? VL is greater than
Greater.
VS. Inductor is releasing the energy. Inductor voltage is negative and inductor voltage is greater than that of the supply voltage. Inductor voltage is negative means, please listen, inductor voltage is actually we consider polarity plus here minus here for inductor na. And
Yes,
if
sir.
this with this polarity, if inductor voltage is negative, the meaning is actually the inductor polarity is like this, voltage across inductor is plus here minus here. Now this voltage is greater than that of this voltage. So what about the voltage across thyristor? Definitely that will be greater than that of your, that will be positive only na. You can simply apply KVL to this loop.
Okay, sir.
VS is less than that of the VL. This is the one thing.
Yes, sir.
If VS is less than, you can check now for VL negative is appearing at the cathode, right? And this, suppose this VS is, let us consider a 5 volt, and suppose VL is, let us consider as a 20 volt. If this is 5 volt, if this is 20 volt here with this polarity, I am saying, what about the thyristor, forward or reverse bias?
Forward.
Forward. So that's why thyristor will be in a conduction mode, right?
Okay, sir. Sir, this condition will be considered in only with R load, sir.
Which condition?
We are considering, sir, after beta also it going to have some energy to release, no, sir.
Inductor.
Inductor.
Ah, yes.
Only this will applicable to with L load also, sir.
Pure inductor.
With L load also we can use this condition there, sir.
Ah, yes, we are using in the L load also. You can check na in the L load what is happening. If you consider the diode rectifier, in the yesterday session we discussed na. During
Yes,
0 to pi, inductor was storing the energy.
Yes, sir.
And after pi, inductor was releasing the energy. And there also after pi, supply voltage was negative na. Even
Yes,
though the
sir.
supply voltage was negative, but inductor was releasing the energy in opposition to that of the supply voltage.
Yes, sir.
Right, same thing was happening, but in the pure inductor case, this theta will not be there. In RL load, the theta will come here. Are you getting the point?
Yes, sir.
Right? Why this theta is coming here? Because of this your VR, voltage across resistor na, we are having the theta concept here. In the pure inductor load, we don't have resistor R.
Yes, sir.
So no point of VR, right?
Okay, sir, understood.
So whatever the V0 in the pure inductive load, whatever V0 is there, right, is nothing but your same as of the supply voltage, and V0 is nothing but voltage across inductor. And supply voltage is positive from 0 to pi. So if supply voltage is positive from 0 to pi, so VL is positive only. VL positive means inductor stores energy. And similarly from pi to 2 pi we are having, right?
Yes, sir.
Okay.
Okay, sir.
Sir,
Hello, sir.
Ah, yes, please.
sir, I have one doubt in yesterday and today question, sir.
Ah, yes, please.
Sir, yesterday we in single phase half wave uncontrolled rectifier with L load, the discharging was from 0 to 2 pi, sir.
What? Please repeat. Please repeat.
And in purely inductive load in half wave rectifier, yesterday we discussed, no, sir.
Third, na?
In that the I naught is discharging until 2 pi, sir. I mean energy is released till 2 pi.
Correct.
But here it stopped with beta. Why, sir? Why it doesn't go till 2 pi, or why the beta value it stopped exactly at beta?
Yes. I will tell you, because due to the resistor. If you check the circuit we are having without a resistor means pure inductor.
Sir, okay. With the now also we have derived an expression with purely inductive load. Can you please go that, sir?
Yesterday,
Control directive. Before this, I think so. Here also it stopped at beta, sir.
yes, huh?
But yesterday problem it goes till 2 pi.
Yes.
The current.
Yes. I will tell you, because the thing is, you can check in the yesterday circuit for how much angle inductor was storing the energy.
We didn't mention the angle, sir.
No, from waveform you can check, na.
Yeah, 2 pi, sir. 0 to 2 pi.
0 to pi inductor was storing the energy.
Yes, sir.
0 to pi you can check means it is like inductor was storing the energy till for pi radian, na.
Yes, sir.
So corresponding to pi radian in the yesterday circuit, I am saying corresponding to the pi radian, the time will be more, na, compared to that of this angle pi minus alpha.
Yes, sir. Yes, sir.
This more means what? Inductor has stored more energy.
Okay. So it takes more time to release the energy.
Inductor will take more time.
Okay, sir.
Here thing is inductor is getting less time to store energy.
Okay, sir. So less time.
Inductor will store less energy, right?
Okay, sir. That's it. Thank you, sir.
Okay.
Sir,
Yes, please.
sir, I wanted to ask that the beta in this half wave control rectifier with purely inductive load is equal to, it is like that pi minus alpha, and in the RL load, for the RL load the beta is not equal to pi minus alpha. This is why.
Okay, why there is a difference, right?
Yes, sir.
You can check here in this circuit. Okay, purely inductive load we are having. In this circuit, when inductor releases the energy, right, whether we are having another element to absorb the power, to absorb the energy, no. Means inductor is releasing the energy only in opposite of the supply voltage. But whereas if you compare this circuitry, just a minute, RL load, right? In RL
Yes,
load we are having the resistor present. Yes, resistor is present. So when inductor releases the energy, some part of inductor energy will be consumed by the resistor also, na?
Yes, sir.
Are you getting the point? In the previous case, it was like
Yes.
resistor was not present. In this case, the resistor is present. So here, whatever the energy released by the inductor, some part of that energy will be absorbed by the resistor also. So that's why we are getting some less, right? Instead of that 2 pi, we're getting some less time here.
Yes.
Right?
Hello, sir.
Yes.
During theta to pi duration.
During
current
circuit?
RL circuit, sir.
Yes,
Only
yeah,
this circuit.
yes.
In the duration theta to pi, I0 decreases or increases, sir?
I0 decreases.
Why, sir? There should be
Because
addition
theta
of
to pi
supply
is
energy
releasing
and
the energy.
inductive energy.
From theta to pi, inductor is releasing
Yes,
the
sir.
energy.
Yes, sir. Releasing energy, but supply energy and inductive energy should be adding, sir.
No,
told us
supply
during that
energy and
previous
inductor
class,
energy
sir.
are adding. Listen me, supply energy and inductor energy are adding. But you can check what is the supply energy. It is a decreasing, na?
Yes, sir.
Supply energy, supply voltage decreasing means supply energy is decreasing.
Yes, sir.
Supply energy decreasing, so inductor is also releasing the energy. So what about your resultant energy? It will be decreasing only, resultant current decreasing only.
Yes, sir. Previous in previous class, you told that in case of single phase half wave uncontrolled rectifier,
Please,
that
please speak up louder.
in previous class, sir, in single phase half wave uncontrolled rectifier,
Huh.
you told that from theta to pi, I0 current should be increases.
From theta to
Pi in case of half wave uncontrolled rectifier with RL load.
uncontrolled rectifier with the RL load.
Yes, sir.
No, we are having the waveform. You can check.
And you told that reason that, sir, supply energy and inductance energy is adding, sir. So due to that, I0 should be increases.
No, when you can check the waveforms also yesterday sessions.
Yes, sir.
This waveform of yesterday session is like this only, na?
No, sir, it's increasing, sir.
Means from theta to pi we have shown increased.
Yes, sir.
Let me open it. Just a minute, I am opening it.
Okay, sir.
Yesterday's marks 27, today's 28, right? Okay. Right. RL load, na?
Yes.
Here it is. Where it is increasing from theta to pi? Till theta only it is increasing. After that it is decreasing, na?
Yes, sir, but you told that increasing, sir.
No, man. No. This is a decreasing only theta to pi. Right?
Okay, sir.
Right.
Okay, sir.
Okay.
Thank you, sir.
Yes.
Hello, sir.
Yes, please. Hello. You are
Regarding yesterday's class, uncontrolled rectifier. Hello, sir. Can you hear me now?
Yes, please.
Sir, uncontrolled rectifier with purely inductive load.
Uncontrolled with purely inductive.
Yes, sir. No need to open that. I just wanted to ask that at the interval from pi to 2 pi, the voltage मतलब इस साइड भी हमारे पास Vs है और उस साइड भी Vs रहता है. VL में V नॉट इज आल्सो इक्वल्स टू माइनस Vs. तो अगर मतलब V आउटपुट के हिसाब से डायोड को देखते हैं तो ठीक है, वो फॉरवर्ड बायस रहती है, लेकिन अगर सोर्स के हिसाब से देखते हैं तो वो रिवर्स बायस्ड होनी चाहिए ना, और दोनों साइड वोल्टेज भी इक्वल है. तो हमने ये कैसे डिसाइड किया कि वी आउटपुट के हिसाब से ही उसको फॉरवर्ड बायस ही मानना है?
Okay. Now the thing is, during pi to 2 pi, V0 आपका Vs क्यों आया है? क्योंकि डायोड कंडक्शन में है.
यस सर.
तो आपका क्वेश्चन क्या है? एक्चुअली डायोड कंडक्शन में क्यों है, एक क्वेश्चन है. सो यहाँ पे ये मत लीजिए कि V0 इज इक्वल टू Vs है, तो इधर भी Vs है इधर भी Vs है, तो डायोड ऑन कैसे होगा? ओके, सो forget about V0. Okay, now what is happening here? Purely inductive load, if you check, first thing is 0 to pi इंडक्टर ने एनर्जी स्टोर किया है.
यस सर.
आफ्टर पाई इंडक्टर रिलीज कर रहा है एनर्जी.
यस सर.
राइट. सो इंडक्टर एनर्जी रिलीज कैसे कर रहा है? इन अपोजिशन टू दैट ऑफ द सप्लाई वोल्टेज कर रहा है.
यस सर.
और जब इंडक्टर एनर्जी रिलीज कर रहा है तो उस सर्किट में उस एनर्जी को कंज्यूम करने के लिए दूसरा कोई एलिमेंट प्रेजेंट है क्या? जैसे रजिस्टर वगैरह कोई नहीं है.
सर.
तो वट एवर द इंडक्टर एनर्जी है, राइट, वो क्या करेगा कि सप्लाई के एनर्जी के अपोजिशन में चला जाएगा. डायोड क्यों फॉरवर्ड बायस है? लेट मी टेल यू. यस, प्योरली इंडक्टिव ना. यस, हियर इट इज. इन दिस सर्किट आप देखोगे 0 टू पाई डायोड कंडक्शन में नो प्रॉब्लम, राइट. इंडक्टर ने एनर्जी स्टोर किया है. सो V0 मतलब इंडक्टर का वोल्टेज था, वो पॉजिटिव था. पॉजिटिव है यहाँ पे. यस और नो?
यस सर.
फर्स्ट थिंग इज V0 इज इक्वल टू वोल्टेज अक्रॉस इंडक्टर है. इज दिस ओके?
यस सर.
ओके, तो ये पॉजिटिव है मतलब इंडक्टर ने एनर्जी स्टोर किया है.
यस सर.
तो पाई क्या हो रहा है? ये इंडक्टर जब एनर्जी रिलीज करता है, ओके, तो हम क्या करते हैं कि पोलैरिटी एज इट इज रखते हैं, प्लस ईयर माइनस ईयर, बट एक्चुअली ये वोल्टेज नेगेटिव होगा, मतलब यहाँ पे प्लस और यहाँ पे माइनस होना है। प्लस यहाँ पे माइनस मतलब क्या है, ये इंडक्टर और इंडक्टर का वोल्टेज और सप्लाई का वोल्टेज एक दूसरे के अपोजिट है। ये अगर अपोजिट है एंड यू कैन चेक, यहाँ पे देखिए इसका एनर्जी तो धीरे धीरे बढ़ता जा रहा है, सप्लाई का एनर्जी, सप्लाई का वोल्टेज धीरे धीरे इंक्रीज हो रहा है ना आफ्टर पाई, बट तब तक क्या है, आपका इंडक्टर का एनर्जी ज्यादा है, इंडक्टर का वोल्टेज ज्यादा है, सो रिजल्टेंट आपका क्या होगा, इसी लूप में करंट फ्लो होगा। एंड वन मोर
सर, इंडक्टर का एनर्जी ज्यादा कहाँ है, मतलब वेव फॉर्म में तो सेम ही दिख रहा है दोनों का।
आप बताइए मुझे कहाँ पे वेवफॉर्म में आपको इंडक्टर का एनर्जी दिख रहा है?
सर ये जो वी आउटपुट है ये अच्छा ये वोल्टेज का है, ठीक है
हाँ
सर।
हाँ हाँ,
ओके सर। सर लेकिन मतलब ऐसा क्यों है, जैसे कि सोर्स से ही तो इंडक्टर ने एनर्जी ली है,
एनर्जी के फॉर्म में
भी
ध्यान में रखिए,
उसकी
एनर्जी
ज्यादा,
मतलब क्या रहता है, इंडक्टर का एनर्जी मतलब क्या रहता है कि हाफ इंटू एल स्क्वायर है ना।
यस सर, तो
तो
वो
इंडक्टर की
एनर्जी
जाने वाला
सोर्स
करंट
से भी
कौन सा
ज्यादा
है?
हो सकती है,
इंडक्टर की एनर्जी
सोर्स से भी ज्यादा हो सकती है, मतलब सोर्स से ही तो उसने एनर्जी ली है, तो इंडक्टर की सोर्स से ज्यादा हो सकती है एनर्जी।
सोर्स से उसने एनर्जी लिया है और उसका एनर्जी सोर्स से ज्यादा हो सकता है। ज्यादा मतलब ओवरऑल नहीं बोल रहा हूं मैं, बट उस पर्टिकुलर इंस्टेंट के वक्त वो ज्यादा हो सकता है। फॉर एग्जांपल समझ लीजिए इंडक्टर का एनर्जी क्या है, हाफ इंटू एल स्क्वायर है।
यस सर।
तो एट पाई देखिए करंट I0 इतना ज्यादा है, सो इंडक्टर का एनर्जी क्या होगा, पीक पे होगा।
यस सर।
राइट, ये अगर पीक पे है तो पाई को सप्लाई वोल्टेज आपका इतना है, कम है, 0 है,
ओके सर।
तो सप्लाई का एनर्जी डेफिनेटली लेस होगा इसके थ्रू कंपैरेटिवली।
ठीक है सर, मतलब इस इंस्टेंट पे इंडक्टर की एनर्जी ज्यादा है, ओवरऑल ऐसा नहीं होता है ना।
हाँ, वो रिस्पेक्टिव इंस्टेंट पे ज्यादा है। ऑल टुगेदर अगर हम देखेंगे, क्योंकि सोर्स ने जितना एनर्जी सप्लाई किया उतना ही इंडक्टर को स्टोर करना चाहिए, राइट।
यस सर।
तो रिस्पेक्टिव मतलब वो इंस्टेंट टू इंस्टेंट अगर हम देखेंगे तो इंडक्टर का ज्यादा है, सो दैट्स व्हाई कंटिन्यूअसली कंडक्शन में चल रहा है, राइट।
ओके सर, थैंक यू सर।
यस, हाँ यस, नेक्स्ट अक्षय, हाँ प्लीज अक्षय।
Sir, this is a general doubt. Like in RL load case, yesterday we mentioned that extinction angle beta, right?
Okay.
The definition we said that was it is the angle till which the inductor releases the energy.
Yes.
So like my doubt, and that beta should be taken from 0, right, sir? You mentioned that you shouldn't take pi minus beta. That is wrongly mentioned in some books. Theta,
No,
yeah.
the thing is, beta is nothing but extension angle. It indicates the instant till which inductor releases the energy. So inductor is releasing the energy till beta, na?
Okay, sir.
So we have to consider from 0 till beta.
Okay, sir. The doubt is like in that 0 to beta gap, the inductor stores energy as well as releases energy, right?
Yes, yes, yes.
So like angle till which it releases energy, then I got the doubt. So
no, angle during which don't keep it in mind. Please keep it in mind in the way the instant till which.
okay, the final instant.
During which means that will be some confusing. Okay.
Okay, sir. Got it. Thank you, sir.
Hello, sir.
Yes, please.
Sir, I had a doubt in today's L load. Sir, uncontrolled rectifier. Sorry, control rectifier. Half wave with L load.
Okay. Just a minute. Okay, what is your doubt?
Sir, when do we tell that this inductor is actually releasing energy? I not get that point, sir.
Okay. Yes, L load, na?
Sir.
Yes.
Sir, when do we tell that this inductor actually starts releasing energy? That
When we
I not understand that. When do we tell that this inductor, whatever energy it is stored, it has started releasing? Like, how do we know that, sir? I not understand.
okay. The thing is, please listen. Inductor stores energy means VL is positive. Voltage across inductor is positive.
Yes, sir.
Okay, so you can check here from alpha till pi. From alpha till pi, Vs is positive.
Yes, sir.
Thyristor is in a conduction mode.
Yes, sir.
V0 is positive. Same as the supply voltage, na V0.
Yes, sir.
So V0 positive means inductor voltage is also positive because in load we are having inductor only.
Yes, sir.
So V0 positive means voltage across inductor is positive. So it is from alpha to pi, VL is positive means inductor is storing the energy.
Okay, sir.
After pi you can check supply voltage is negative.
Yes, sir.
But whether our inductor will allow the sudden reversal of the current. Sudden reversal I am using the word why, because at pi you can check current through the inductor is positive and high value na.
Yes, sir.
But suppose if inductor is not opposing to the change in the current, then it is like resultant current will be anti-clockwise or thyristor will be in off state.
Yes, sir.
Suddenly whether that current will be become zero? No, because our inductor will not allow that, right? So that's why our inductor will release energy.
Sir.
So after pi, when inductor releases the energy, you can check the voltage across inductor, that is a V0, it is a negative.
Sir.
So it indicates negative voltage means inductor is releasing the energy. Positive means inductor is storing the energy.
Sir, so from this waveform only we can tell that, sir. Otherwise we cannot tell. Only because VL is positive, like that we are telling.
No. From this also you can tell whatever the expression we have derived now. From this expression also you will understand.
Okay.
Because you can check here, you can put the value of omega t. First alpha, after that put pi by 2. After that you can put pi radian. After that 3 pi by 2 you can put and like this. Okay. Select any value of alpha. Let us consider alpha 30 degree. And after that you can put values of omega t. Right. So then draw the I0 waveform. You will be getting I0 waveform is like this. Okay.
Sir.
So for up to some part it will be increasing. Increasing means it is the inductor storing the energy only. Or you can check di by dt also here, na?
Sir.
Di by dt positive, here di by dt is negative.
Sir.
Right. So in this way we can understand.
Okay.
Otherwise, how to find how inductor is storing the energy and releasing the energy, right?
Okay.
Or you can take the product of these two also, you will understand. One is positive, this is positive, okay? Increasing and this is positive, means energy will be positive or power will be positive. This is negative, this is positive. If you take the product, negative power means one is storing energy, second interval it is releasing the energy, right?
Okay, sir.
Okay.
Sir, and other doubt is in this RL load, why can't that theta be equal to pi, sir? Why is it always less than pi?
In RL load?
We have taken, you told that theta is always less than pi, that theta when it's charging, but why, sir?
Yes.
Why can't it be like pi?
Just a minute, let me open it, that RL load, no?
Sir.
Okay. Yes, RL load. Okay. Why theta is less than pi? Because the theta indicates the instant till which inductor is storing the energy.
Yes, sir, but why can't it be like, why can't we take it till pi, or why can't theta be equal
For
to pi?
that also the reason is VL only, voltage across inductor. VL positive, inductor stores energy.
Sir.
So you can check here, this red vertical lines, na?
Sir.
This indicates your VL.
Okay.
At alpha, what is VL? We know na, VL means what? VL is equal to Vs minus VR, na?
Sir.
So if Vs is at alpha, Vs is this much and VR is 0.
Sir.
We have drawn VR from I0.
Sir.
Now you can check here. At alpha VR is 0, Vs is this much value. So what is Vs minus Vr? It is this much value of VL.
Sir.
Voltage across inductor is high value now.
Yes, sir.
After that, you can check here Vs is increasing, Vr also increasing. And the difference between the two will be your VL. So you can check from alpha till theta. From alpha till theta, what is happening? VL is decreasing na?
Yes, sir.
It was a high here and here it is a 0. At theta, VL is 0. So it is like your VL is positive here. Inductor has stored the energy till theta. After theta, what is happening? After theta, you can check VL is again Vs minus Vr. After theta, your Vs is less than Vr.
Sir.
So Vs is less than Vr means VL is negative.
Yes, sir.
And what is the magnitude of VL? This is the magnitude of the VL. So VL is negative means what? After theta, inductor is releasing the energy. So whether your point theta is before pi or after pi, it is before pi only na.
Sir.
So that's why till theta it is like inductor is storing the energy only. And always theta is, for RL circuit, your theta is always less than pi only.
What will happen, sir, if it is equal to pi? Can't there be a situation like that?
No, it is not possible even. It is equal to pi for purely resistive load. It is not possible. So in that case, the thing is you need to keep the value of resistor is very, very small. It is a negligible.
Okay.
Then and only then it is possible.
So it's because of this R. It's because of this R that we are having theta and before pi.
Yes, because of the resistor only it is happening. You can check na, in a purely inductive load means when resistor is not. So in that case, it is like theta is equal to pi only. So in the purely inductive load, it is like theta is pi. But in this case, it is not possible. Right?
Sir.
Okay.
Sir, and one last doubt. Can you take page 40?
Okay. Page 40.
40.
Yes.
Sir, in this, when we finally calculated, we got this voltage across this freewheeling diode as 0, sir, that we got from this.
Yes.
But then we have shown it as open circuit also. So usually in open circuit, high voltage should.
No, it is not like that. Across open circuit is the voltage is high. No, voltage across open circuit depends on across which terminals. Okay, this open circuit is connected. You can check. You can apply KVL to this loop.
Sir.
The minus VDF minus V0 is equal to 0. So minus VDF minus V0 0 means your V0 is 0 already.
Yes, sir.
So it is like minus VDF minus 0 is equal to 0. So what is VDF? 0 only na?
Sir. So it's like even if it is open, if 0 volt is coming across, it's not a problem.
When if
usually if diode is like if the freewheeling diode has 0 volts across it, we tell that it's conducting, sir.
If 0 voltage is there, then no. It is not like that. Actually, if the voltage across diode is positive, then it starts conduction. And due to its conduction, that voltage across the diode will be 0. Suppose if from market if I purchase from market if I purchase a diode,
sir.
And that diode, suppose I have not connected any supply to that diode. So it is like voltage across diode is 0 only. So whether your diode will be in a conduction mode, no na?
Oh no.
It depends. Okay.
Yes.
After conduction, that voltage will be 0 definitely. But now the situation like here it is open circuit, here it is open circuit. At both the sides we are having open circuit. Current is not flowing here. Voltage across diode is equal to voltage across load only. Right? And always keep it in mind, it is not a thumb rule like open circuit voltage is always very high. No, it depends on, right, across that open circuit which terminals we are having. Means suppose in your house you might be seeing that we are having the plug, na, single phase plugs.
Sir.
If you turn on the switch and if you check the multimeter, then across that open circuit it will show the 230 volt. Why it is showing 230 volt? Because backside of that we are having the single phase supply is coming there, na. So that's why it is 230. Right? So it depends actually. Okay.
Okay, sir.
Right.
Understood.
Right.
Thank you, sir.
Yes. Okay. Next, Pratik Bhosle, Shravan Kumar, Moka, Baby Kavya. Do you have any doubt? Yes, just a minute.
Hello, sir.
Yes, please.
Sir, how to calculate RMS power, sir?
How to calculate?
RMS power, sir.
RMS power.
We should not calculate any.
For which?
For every circuit, we are calculating IRMS and
RMS power means it is a part of the AC circuit. In the AC variable, na, VS RMS into IS RMS, V into I into some power factor angle. That will be your RMS power.
Okay.
Are you getting the point? In a rectifier case, right? In the load, we don't have concept like RMS power.
Okay, sir. Can we
Right?
calculate or cannot calculate, sir? Cannot able to calculate.
Yes, yes.
Can we calculate the RMS power, sir?
For supply, we can calculate, na?
Okay.
For
sir.
supply, RMS power means your VS RMS into IS RMS into cos phi s.
Okay, sir.
But in rectifier, both powers are same, na?
Yes, sir.
So in the load, if you want, you can say it as average power. From the source point of view, if you want, you can say it as RMS power, right?
Okay, sir. Thank you, sir.
Yes, next.
Hello, sir.
Yes, please.
37F, sir.
37. Okay.
Sir, here theta value is V0 and I0 are coincide value, na, sir?
Theta value?
Here V0 and I0, both are coincide.
Both are coinciding. Both are coinciding.
That one is theta value, sir?
Yes.
Okay,
Both
okay.
should be coinciding here. Okay.
Okay.
I think it should be from here only. Right?
Okay, sir.
Any other doubt?
Sir, once explain threshold means, sir. Threshold.
What?
Threshold value means, sir?
Where it is given?
General doubt, sir. My general doubt, threshold value.
Will you please state that means question that threshold value where they have asked?
Other subjects at this one not.
No. Yeah, tell me that subject question. Don't no problem.
Sir, I think it's from MOSFET, sir.
Yes.
MOSFET.
Okay.
We told him.
MOSFET wearing the threshold value. Okay. I am thinking where in this circuit where the threshold will come. Okay. So MOSFET in the MOSFET wearing the threshold value means actually the thing is suppose when the manufacturer constructs one device now, then it gives that threshold value. What that indicates, and that threshold value depends on your device construction and the device depletion layer and the doping percentage also. Okay. In the MOSFET, we are having the concept like if VGS is less than VGS threshold, then MOSFET will be in a cutoff region. Means if we want to turn on the MOSFET, then the minimum required voltage should be greater than whatever the specified by the manufacturer. That is the threshold value.
Okay. Threshold means highest value, sir?
No, minimum value it is.
Okay,
In
sir.
order to turn on the switch, we require that minimum value, na? Otherwise the device will be in a cutoff region.
Okay,
right?
Sir. Okay. Thank you, sir.
Yes. Okay. Thank you. Thanks to all of you.